Hello there, and welcome to the Cosmographer. On the 9th of March 1979, a navigation engineer at the Jet Propulsion Laboratory brought up a photograph that had been deliberately overexposed in order to ignore the moon at the center of it, and found a cloud 250 kilometers tall hanging off its edge. That is number 9 on this list, and it is the moment a human being first saw a volcano erupting on another world. Number 13 is a cliff so tall that stepping off the top of it takes somewhere between 8 and 12 minutes to reach the bottom. Number 7 is a surface at 38 Kelvin, the coldest ever measured anywhere, and it has geysers on it. Number 4 is the outer boundary of the Sun's territory, 18 billion kilometers out, which was proved using a workaround for an instrument that had already been broken for 32 years. Over the next 3 hours, we count down 20 things the Voyager probes saw, ordered by how badly each one broke the assumption that the solar system was already understood. Get comfortable and settle in. If falling asleep to the outer solar system is your idea of a good night, a quiet like and subscribe genuinely helps this channel reach more people who feel the same way. Because the thing at the top of this list was photographed 34 minutes before the cameras were switched off forever, and it is not a planet. Let's begin at number 20. Number 20, the ring that appeared to be braided. In August and September of 1977, 2 machines left Earth 11 weeks apart. Between all 6 of their computers, they carried 69.5 kilobytes of memory, which is less than 1/100th of the memory in a modern greeting card that plays a song. They were built for a 4-year mission to Jupiter and Saturn. They are still transmitting. What those 2 spacecraft sent back is the largest single expansion of the known solar system in human history. Before them, everything past the asteroid belt was 5 bright points of light and a scatter of pinpricks around them. After them, it was a catalogue of worlds. One of them is melting itself alive. One of them has more liquid water than Earth. One has a cliff so tall that falling off it takes several minutes. One is colder than anything anyone has ever measured, and it is still geologically active. Almost none of it was expected. A great deal of it is still unexplained. Over the next 3 hours, we are going to count down 20 of the things the Voyager probes saw, from number 20 to number 1. The order is not distance, and it is not fame. It is how badly each observation broke the assumption that the solar system is a settled, finished, well-understood place. The early entries are strange structures. The middle entries are violent worlds. The last few are about us. We begin at Saturn, with a ring that is doing something rings are not permitted to do. Saturn's F-ring sits about 140,000 kilometers from the planet's center, just outside the bright main rings, and it is narrow. In places, it is only a few hundred kilometers wide, and in places it narrows to under 100. That is a lane of material thinner than the length of many countries, wrapped in a circle around a planet 9 times the width of Earth. Voyager did not discover it. Pioneer 11 found it in September of 1979, and it was so faint and so narrow that Pioneer's instruments barely registered it at all. It was very nearly written off as noise. What Voyager 1 did on the 12th of November 1980, from a range of about 750,000 kilometers, was resolve it properly with the narrow-angle camera. The images did not show a ring. They showed several strands running alongside each other, and the strands appeared to cross over one another. They were kinked. They were knotted at intervals. The whole structure looked, as plainly as anything in the mission's archive looks like anything, as though someone had taken a rope and plaited it. That is a problem, and it is worth being precise about why. A planetary ring is not a solid object. It is billions of independent particles, and every one of them is on its own orbit around Saturn. Particles closer in travel faster than particles farther out. That difference in speed, over any distance at all, shears the ring apart along its length. It is the same reason cream stirred into coffee does not stay in a spiral. Anything twisted together in a ring should be pulled straight within a few orbits, which at Saturn means hours to days. So a braided ring is a structure that should not survive long enough for a camera to arrive and photograph it. The Voyager imaging team published the observation without an explanation because there was not one, and the phrase braided ring entered the scientific literature as the name of something nobody could account for. There were two other objects in those images. On approach, in October of 1980, the imaging team found a pair of small moons flanking the F-ring. One sat just inside it, one just outside. They were catalogued at the time as S1980, S27, and S1980, S26, and named 5 years later. The inner one is Prometheus, with a mean radius of about 43 kilometers, orbiting at 139,000 kilometers with a period of 14.7 hours. The outer one is Pandora, mean radius about 41 kilometers, at 142,000 kilometers with a period of 15.1 hours. Both are small enough to fit comfortably inside Greater London. Both are irregular, potato-shaped, and heavily cratered. And for roughly 40 years, they carried the explanation. The account that went into every textbook was elegant. The inner moon passes ring particles and speeds them up slightly, pushing them outward. The outer moon passes and slows them down slightly, pulling them inward. Between the two of them, the ring is herded into a narrow lane it cannot escape. They were called shepherd moons, and the word shepherd did a great deal of work in a great many classrooms. That explanation is now known to be wrong in its details, and the correction came in two stages. The first stage was Cassini, which spent 13 years at Saturn and looked at the F-ring at resolutions Voyager could not approach. What Cassini showed is that the ring is not several strands. It is one long spiral, wound at least 3 times around the planet, and the apparent braiding is the work of Prometheus alone. Every 14.7 hours, at its closest approach, Prometheus reaches into the ring's inner edge and draws material out into a streamer, leaving behind an empty channel. Orbital shear then stretches and wraps those streamers, and what a camera at Voyager's resolution sees is strands crossing over each other. The ring carries a regular series of these scars, each one the record of a previous close pass. The second stage came in May of 2024. A reanalysis concluded that Prometheus confines the F-ring essentially on its own, through an orbital resonance, and that Pandora is not a shepherd at all. It also concluded that the confinement is intermittent. A chaotic wobble in Prometheus's own orbit disrupted the arrangement late in the Cassini mission. The two moons are in a dynamical relationship with each other that cannot be predicted accurately more than a few decades ahead. And there is one more detail, which is the reason this entry opens the list rather than being left out of it. When Voyager 2 arrived at Saturn 9 months after its twin, in August of 1981, the F-ring looked different. The strands were in a different configuration. Whatever the structure is, it does not hold for a year. Which means Voyager 1 photographed a temporary arrangement of matter in a ring made of ice grains roughly a micrometer across, and there is no particular reason to believe that exact arrangement has ever occurred again in the 4.5 decades since. That is the shape of everything on this list. A thing photographed in perfect detail, catalogued, named, given a page in a textbook, and still, 45 years later, not properly explained. It is worth pausing on what the F-ring is actually made of, because the material matters. It is predominantly water ice, in grains around a micrometer across. That is closer to smoke than to gravel. A ring made of particles that small is exquisitely sensitive to anything that touches it, which is why a single small moon passing at a distance can leave a mark that lasts long enough to photograph. Cassini also found something inside the ring that Voyager could not have resolved. Small trails of material, nicknamed mini-jets, produced when objects roughly a kilometer across, embedded in the ring, collide with the surrounding material at speeds of a few meters per second. A few meters per second is walking pace. In a ring, this fine walking pace is enough to throw up a plume that stays visible. And the ring itself is not constant in brightness. Comparisons between the Voyager-era images and the Cassini-era images suggest the F-ring was significantly brighter in 1980 than it was in the 2000s. Something has changed in the intervening decades, and nobody is entirely sure what. The F-ring at least holds its shape. The next thing Voyager photographed at Saturn draws itself across the rings in a matter of minutes, and then it disappears. Number 19. The shadows that move with the magnetic field. In approach images taken in October of 1980, before it had even reached the planet, Voyager 1 photographed something lying across Saturn's outer B-ring that had no business being there. Dark markings, running radially, pointing straight outward from the planet, like the spokes of a wheel. That is what they were named. Each one is roughly 10,000 kilometers long and about 2,000 kilometers wide. 10,000 kilometers is close to the diameter of the Earth. So the image is of a smear the length of our entire planet, laid across the rings the way a finger is drawn through dust on a table. They form in minutes. They last a few hours. Then they are gone. The reason this is strange is the same reason the braided ring is strange, only worse. The rings are not a disk. They are independent particles on independent orbits, and inner particles move faster than outer ones. A radial feature, a line pointing straight out from Saturn, is precisely the shape that differential rotation destroys fastest, because every part of the line is being carried at a different speed. A spoke should curve, then smear, then vanish within a single rotation of the ring. Voyager watched spokes hold their radial shape while rotating. And then Voyager measured how fast they were rotating, and the answer made it worse. Fresh spokes rotate at roughly the same rate as Saturn's radio emission. Voyager measured that radio period at 10 hours, 39 minutes and 24 seconds. Older spokes settle down and start moving the way everything else in the rings moves, on ordinary orbits. So a spoke begins its life keeping time with the planet's magnetic field, and then, after a few hours, gravity takes over and it dissolves. That is a genuinely odd result, because the radio period has nothing to do with the rings. It is set by Saturn's magnetic field, deep inside the planet. Something in the ring plane was being carried by magnetism rather than by gravity, and the something in question is made of dust. One correction is worth making here, because that 10-hour, 39-minute figure has been misquoted for decades. It is the radio period, and it is not Saturn's rotation period. It drifted by several minutes in the years after Voyager, and it eventually split into separate northern and southern values, which a planet's rotation cannot do. Saturn's true internal rotation was only pinned down much later by reading oscillations in the rings themselves, and it comes out at 10 hours, 33 minutes and 38 seconds. The leading explanation for the spokes is electrostatic, and it has been the leading explanation since roughly 1982. The idea is this: among the boulders and chunks of ice that make up the rings, there is a population of extremely fine grains, around a micrometer across, which is the size of a smoke particle. If those grains acquire an electric charge, they can be lifted clear of the surfaces they were sitting on and held briefly above the ring plane. Suspended dust scatters light differently from the ring behind it. Looking at the rings from one direction, the levitated dust appears dark, and from the other direction, it appears bright. Voyager saw both, which is one of the strongest pieces of evidence for the whole picture. What nobody can settle is what charges the grains in the first place. One candidate is micrometeoroid impacts, which produce small clouds of plasma when they strike the ring. Another is lightning in Saturn's atmosphere, driving beams of electrons up onto the rings along magnetic field lines. Neither has been confirmed. A full review of the spoke problem published in 2024 stated the position plainly. None of the theoretical ideas have been fully tested. Cassini did add something Voyager could not, and it is a strange addition. The spokes are seasonal. Activity climbs when the Sun sits within about 10 degrees of the ring plane and falls away as the rings tilt toward the Sun. Between roughly 1998 and 2005, the spokes disappeared entirely, an absence recorded by the Hubble Space Telescope, and then they came back. When Cassini arrived, there was real uncertainty about whether it would ever see one. Its first spoke sighting came on the 5th of September, 2005. There is also a small footnote that is easy to miss. An amateur observer named Stephen O'Meara reported seeing radial markings on Saturn's rings, visually through a telescope in 1976. 4 years before Voyager. The reports were not taken seriously at the time. So the position as it stands today is this. The most photographed ring system in the solar system, observed continuously for 45 years by 2 flyby spacecraft, one orbiter that stayed for 13 years, and a space telescope, draws shapes across itself that appear in minutes, keep time with a magnetic field rather than with gravity, and disappear. And there is no confirmed account of what makes them. There is one more piece of the geography worth fixing in mind, because the spokes do not appear anywhere they like. They occupy a specific band, roughly 105,000 to 117,000 kilometers from Saturn's center. That is the outer part of the B ring, and essentially nowhere else. Whatever conditions produce them exist in that band and stop at its edges. The speed is the other detail that resists explanation. Individual spokes have been observed forming in under 5 minutes, across thousands of kilometers. Nothing in the rings moves that fast relative to anything else in the rings. Whatever propagates the pattern is not traveling with the material. It is traveling through it. The B ring itself does not help. It is the densest of Saturn's rings, dense enough that in places it saturates the instruments trying to measure it, which means the region where the spokes live is also the region where the ring is hardest to characterize. There is an unhelpful symmetry in that. The most unexplained feature sits in the least measurable place. Voyager 2 confirmed the spokes independently in August of 1981 and refined the measurements of how long they last. 2 spacecraft, 9 months apart, both saw them, both timed them, and neither could say what they were. The rings, at least, are built to be rearranged. The next entry is a moon that came very close to being rearranged permanently. Number 18. The crater that almost finished a moon. On the 12th of November 1980, the same day it photographed the Braided F ring, Voyager 1 passed 88,440 kilometers from Mimas, the innermost of Saturn's major moons. What came back is one of the most recognizable images in the entire archive, and it is recognizable for a reason nobody involved intended. Mimas is 396 kilometers across. That is small enough to fit inside Spain. It is made mostly of water ice with a little rock mixed in, and its density, about 1.15 grams per cubic centimeter, is barely above the density of ice itself. Mimas is, in the most literal sense available, a dirty snowball. Set into one face of that snowball is a single impact crater about 130 to 140 kilometers across. The crater is named Herschel, after William Herschel, who found Mimas on the 17th of September, 1789. The name was given by his son John. Its exact diameter is genuinely disputed, and the dispute runs through NASA's own published material. The United States Geological Survey Gazetteer and several image captions give 139 kilometers. NASA's own Mimas page and other captions give 130. Both figures are official. The honest statement is that Herschel is somewhere around 135 kilometers wide, give or take. Whichever number you take, it spans about a third of the entire Moon. The walls stand roughly 5 kilometers above the crater floor. The central peak, the rebound mound at the middle where the surface splashed back up after the impact and froze in place, rises about 6 kilometers. The floor itself sits something like 10 kilometers below the surrounding terrain. On a body 400 kilometers across, those are not gentle features. They are a substantial fraction of the Moon's own radius. And that is the point of this entry. An impact large enough to excavate a crater a third of the body's width sits very close to the boundary between cratering something and destroying it. Modeling of the impact suggests the shock wave passed all the way through Mimas and produced fracture systems on the far side, at the antipode, where the seismic energy would have reconverged. Those fractures are visible. The Moon absorbed a blow that nearly went through it, rang like a bell, and stayed in one piece. Marginally. If the impactor had been slightly larger or slightly faster, or had struck slightly differently, there would be no Mimas. There would be a band of ice debris in orbit around Saturn where a moon used to be. And there would be no Cassini division either, because the visible gap between Saturn's A and B rings, the one that is obvious in any small telescope, exists because Mimas maintains it. Particles at that radius orbit Saturn exactly twice for every one Mimas orbit, and that repeated tug clears the gap. Remove Mimas, and the most famous feature in Saturn's rings goes with it. Then there is the other thing about the images, which is that Mimas looks like the Death Star. That is not a comparison invented by the internet. NASA has used it in its own captions, including one titled, without embarrassment, "That's no space station." A grey sphere with one enormous circular dish set into its face, photographed by a spacecraft in 1980, 3 years after the film came out. The resemblance is coincidental and complete. There is a final twist, and it is recent. Mimas should be the least interesting object in the Saturn system. It is small, it is cold, it is saturated with craters, and everything about its appearance says it has been geologically dead since the early solar system. Its surface gravity is about 0.064 meters per second squared, roughly 1/600th of Earth's, which means a person standing on it could jump several hundred meters and take a long time coming down. But Mimas has a libration. As it orbits Saturn every 22 hours and 37 minutes, it rocks very slightly back and forth, and that rocking is far larger than a uniform frozen ball of ice should produce. There are two ways to explain it. Either the interior contains an oddly shaped rocky core, or there is a layer of liquid water beneath 20 to 30 kilometers of ice. The ocean interpretation has strengthened considerably in recent work, and the analysis suggests something stranger still. If the ocean is there, it appears to be geologically young, on the order of tens of millions of years old, rather than billions. Which would mean that the moon that looks the deadest is the one that has most recently come alive. Cassini added one more oddity while it was there. The temperature map of Mimas showed a sharp-edged warm region shaped almost exactly like the Pac-Man video game character, with a crater sitting where the eye would be. Similar patterns have since been found on other Saturnian moons. The explanation involves differences in how the surface was compacted by high-energy electrons, and it is only partly worked out. It is worth dwelling for a moment on what an impact of that size actually involves, because the numbers on their own do not carry it. The object that made Herschel would have been somewhere in the region of 10 kilometers across, arriving at several kilometers per second. On a body with essentially no gravity to speak of, most of the excavated material would not have fallen back. It would simply have left, thrown clear of the Moon entirely, and scattered into orbit around Saturn. A substantial fraction of Mimas is not on Mimas anymore. It is somewhere in the Saturn system, dispersed, unrecoverable, and impossible to identify. There is also a curiosity in the published figures that says something about how measurement works. NASA's own page for Mimas lists its dimensions as 207 by 197 by 197 by 197 by 197 by 197 by 197 by 197. Those numbers are radii, not diameters, which means the Moon's actual triaxial dimensions are roughly 416 by 393 by 381 kilometers. It is a small ambiguity in a caption, and it has propagated widely. Even for a body we have photographed from close range, the numbers in circulation require checking. And Mimas is not spherical in the way it looks. It is measurably stretched along the axis pointing at Saturn, pulled out of shape by the planet's gravity, and flattened at the poles by its own rotation. The distortion is the reason the libration can be measured at all. A perfectly round moon rocking slightly would be very difficult to detect. An egg-shaped one rocking slightly gives itself away. Mimas survived one enormous impact. The next moon on this list has been quietly ruined by something far slower. Number 17. The moon with one bright face and one black one. Iapetus is Saturn's third largest moon, about 1,470 kilometers across, and it orbits far out from the planet, at around 3.5 million kilometers, on an orbit tilted 15 degrees to Saturn's equator. Voyager 2 passed it on the 22nd of August 1981 at a range of about 909,000 kilometers. That is not close. It was close enough. One hemisphere of Iapetus reflects between 3 and 5% of the light that falls on it. That is about as dark as fresh asphalt or coal. The other hemisphere reflects between 50 and 60%, which is about as bright as dirty snow. The two halves differ in brightness by more than a factor of 10, and the boundary between them is sharp. This puzzle is 350 years old, and it is worth telling accurately because the version in wide circulation compresses it into something misleading. Giovanni Cassini discovered Iapetus on the 25th of October 1671, while it sat west of Saturn. In 1672, he looked for it on the eastern side of the planet and could not find it at all. He did not solve the problem then. He simply lost the moon. It was only in 1705, more than 30 years later, and with a better telescope, that he recovered it in the east, roughly 2 magnitudes fainter than he had seen it in the west, and worked out what that had to mean. Iapetus must keep one face permanently towards Saturn as it orbits, and one of those two faces must be very dark. That is where the problem sat, essentially untouched, until spacecraft arrived. What Voyager 2 added was resolution. The images resolved the boundary between the two hemispheres and established that the dark material, later named Cassini Regio, covers the leading hemisphere. That is the side that faces forward along the direction of travel. A pattern like that is the signature of material being swept up, like insects on a windscreen, rather than material being erupted from below. Voyager also photographed a line of bright dots running along the equator, informally called the Voyager Mountains. Nobody could interpret them at the resolution available. It is important to be clear about what Voyager did not see, because this is a frequent error. Iapetus has an equatorial ridge, and it is one of the most bizarre landforms in the solar system, and Voyager did not find it. Cassini did, in approach images around the 24th and 25th of December 2004, and resolved it properly on the flyby of the 31st. The ridge runs about 1,300 kilometers along the equator, stands at least 13 kilometers high, and is about 20 kilometers wide at its base. In silhouette, it makes Iapetus look like a walnut. Its origin has never been explained. The explanation for the two faces, on the other hand, has been found, and it is a good one. Iapetus rotates slowly, once every 79.33 days, locked to its orbital period. That means each hemisphere sits in continuous sunlight for about 40 days at a stretch. Now consider what happens if one region starts out slightly darker than another. The dark patch absorbs more sunlight and warms up. Water ice sublimates off it, migrates through the thin exosphere, and refreezes on the colder, brighter regions. The dark side loses its ice and gets darker. The bright side gains ice and gets brighter. The process feeds itself. It is a thermal runaway, and Cassini confirmed it in September of 2007. That leaves one question. Where does the initial dark dust come from? The answer was found in 2009, and it is enormous. Saturn is surrounded by a ring of debris so wide and so faint that it had never been detected. It was found in the infrared, using the Spitzer Space Telescope, and it is shed by the outer moon Phoebe, which orbits Saturn backwards. The ring is so large that if it were visible to the naked eye, it would cover a patch of sky many times wider than the full moon. Iapetus is plowing through it. It has been plowing through it for billions of years, collecting dust on the face that leads. The coating that results is a few tens of centimeters thick at most. Everything about the appearance of Iapetus, the feature that defeated a 17th century astronomer and stayed unexplained through the space age, is a layer of dust you could scrape off with a shovel. At high resolution, the boundary between the two regions is not even a clean line. It is a ragged transition zone, where dark deposits sit preferentially on the equator, facing walls of craters, exactly as a thermal migration model predicts. Iapetus is otherwise dead. There is no detectable internal activity, and there probably has not been for billions of years. Its only distinguishing feature is a shape it froze into while spinning much faster than it does now, leaving it about 67 kilometers flatter from pole to pole than it is across the equator. The Phoebe ring deserves a moment on its own, because it is one of the largest structures anywhere near a planet, and it stayed hidden until 2009. It is enormous, and it is essentially empty. If you were standing inside it, you would see nothing at all. The particles in it are widely separated, dark and cold, and the only reason it was found is that cold, dark dust glows faintly in the infrared, and a space telescope designed for exactly that wavelength happened to look in the right place. Phoebe itself is worth noting. It orbits Saturn backwards, at a distance of about 13 million kilometers, which is more than 3 times farther out than Iapetus. A moon in a retrograde orbit at that distance did not form where it is. It was captured, almost certainly from the outer solar system, and it has been eroding under micrometeorite bombardment ever since, shedding the dust that Iapetus then sweeps up. So the sequence runs like this. A captured object from the outer solar system, orbiting the wrong way, is slowly being sandblasted into a ring. That ring is invisible. Iapetus, orbiting the right way, drives into it and collects the dust on its leading face. The dust darkens that face by a fraction. The fraction is enough to start a thermal runaway that takes over and does the rest. The result is a moon with 2 faces, which a man with a 17th century refracting telescope noticed because it kept disappearing on him. There is one more piece of trivia that is hard to leave out. Arthur C. Clarke used Iapetus as the location of the alien monolith in the novel of 2001, written years before any spacecraft resolved it. He chose it because it was the strangest object he could find in the astronomical literature of the time. He had no way of knowing he was right about that. Iapetus at least keeps one face toward Saturn. The next moon does not keep any face toward anything. Number 16. The moon that has no rotation period. On the 24th of August 1981, Voyager 2 passed Hyperion at a range of about 431,000 kilometers. The figures attached to individual published frames vary, so it is worth saying loosely, roughly 500,000 kilometers, which for this mission counts as a passing glance. What it photographed in that glance was an object that looked, immediately and obviously, wrong. Hyperion is not a sphere. It is not even an ellipsoid. It is a battered, irregular mass measuring roughly 360 by 266 by 205 kilometers, with a mean diameter around 270. It is one of the largest bodies in the solar system known to be genuinely irregular in shape, and that is unusual because above a certain size, a body's own gravity pulls it round. Hyperion is right at the boundary, and it lost. Its surface is a dense field of deep, sharp-edged craters with almost nothing between them. There are no plains. There is no smooth terrain. The craters sit shoulder to shoulder, and their walls are steep and clean, rather than softened, so the overall impression is less like a rocky landscape than like a sponge or the inside of a bone. Voyager did not discover that Hyperion tumbles. It is important to get this the right way round, because it is a good example of how a flyby result actually turns into knowledge. What Voyager did was measure the shape. The shape is what made the discovery possible. 3 years later, in 1984, an analysis using the Voyager-derived shape showed that Hyperion, given how elongated it is and given its orbital resonance with Triton, could not possibly have a stable rotation. Its spin had to be chaotic. Not merely irregular, not merely wobbly, but chaotic in the strict technical sense. Tiny differences in its present orientation grow exponentially with time, so its future orientation cannot be calculated beyond a horizon of a few months, no matter how precisely you measure it today. Ground-based photometry confirmed the tumbling observationally in 1989. This is worth flagging because NASA's own public page for Hyperion states that it rotates roughly every 13 days. That contradicts the established result and should not be repeated. The correct statement is that Hyperion has no stable rotation period at all. Cassini later measured its spin axis at roughly 30 degrees away from its long axis, turning at between 4 and 4.5 times the synchronous rate, with a predictability horizon of about 100 days. Consider what that means for anyone standing on it. Saturn would not rise and set. It would swing across the sky along a path that never repeated, at a rate that varied, in a direction that changed. There is no day length on Hyperion. There is no fixed sunrise. There is no calendar you could construct, no matter how long you stayed, because the motion is not periodic. It is deterministic, in the sense that the physics is entirely understood, and it is unpredictable, in the sense that the outcome cannot be computed beyond a horizon of a season. Those two things are not contradictory, and Hyperion is the clearest demonstration of it that exists in the solar system. What drives the chaos is Triton. Hyperion is locked in a 4-to-3 orbital resonance with it, which means that for every 4 orbits Hyperion makes, Triton makes 3, and the two bodies return to the same relative positions again and again. Triton is enormous. Hyperion is elongated. Every few orbits, Triton gives the long axis another tug, and because Hyperion is not round, the tug applies a torque. The torques accumulate, and because the system is chaotic, they never settle into a pattern. Then there is the density, which explains the sponge. Cassini's close pass in September of 2005 measured Hyperion's density at 544 kilograms per cubic meter. Water ice is about 920. So Hyperion is roughly half as dense as the ice it is made of, which means it is more than 40% empty space. It is not a solid body. It is a loosely bound rubble pile with voids running through it. That is why the craters look the way they do. When something strikes a porous target, the impact compresses the material inward rather than blasting it outward. There is very little ejecta, so nothing gets blanketed and nothing gets filled in. Craters are punched into the surface and then preserved almost exactly as they were made, one on top of another, for billions of years. Hyperion also collects dark reddish material in its crater floors, chemically similar to the dark material on Iapetus, which makes sense given how close the two moons are and where the dust in that part of the system comes from. A final oddity. When Cassini made its close pass, the spacecraft and the moon exchanged an electrostatic discharge across several kilometers of vacuum. Hyperion had built up a charge. Nobody had planned for that. Hyperion was found in September of 1848, and even its discovery is disputed in a small way. William and George Bond saw it first, on the 16th. William Lassell published first, on the 18th. All three are credited jointly, which is a tidy outcome for a moon whose defining property is that it cannot be pinned down. It orbits Saturn every 21.3 days at about 1.5 million kilometers, which puts it between Triton and Iapetus in the outer part of the system. The word chaotic is used loosely in ordinary speech, and precisely in this context, and the difference matters. A chaotic system is not random. Every step of Hyperion's tumble follows Newtonian mechanics exactly. The problem is that the equations amplify uncertainty rather than damping it, so an error of 1 part in a million in today's measurement becomes an error of 100% within a few months. The technical measure of that amplification is called the Lyapunov time, and for Hyperion, it is around 100 days. That is extremely short. Most chaotic systems in the solar system have Lyapunov times measured in millions of years. So Hyperion sits in an unusual category. It is a body whose motion is fully understood, fully deterministic, and permanently unpredictable, and it is large enough to see from Earth. Everything so far has been at Saturn. The next entry is at Jupiter, and it was found because one person asked for a photograph of nothing. Number 15. The ring system nobody expected to find at Jupiter. On the 4th of March 1979, Voyager 1's wide-angle camera held its shutter open for 11 minutes and 12 seconds, pointed at a strip of apparently empty space near Jupiter's equatorial plane. It was a long exposure of nothing, taken over the objections of people who considered it a waste of a scarce imaging slot on a spacecraft that had a great deal else to photograph. In the returned frame there was a thin, bright line where there should have been nothing at all. Jupiter had a ring. The discovery was announced 3 days later, on the 7th of March. There is a reason someone asked for that exposure, and it goes back nearly 5 years. Pioneer 11, passing Jupiter in December of 1974, had recorded an unexplained dip in charged particles at a particular distance from the planet, as though something at that radius was absorbing them. A paper published in 1976 suggested a ring or belt of material as the explanation. That was the inference that put the possibility on the table. The person who pushed for the exposure on Voyager 1 was Tobias Owen, a co-investigator on the imaging team. The imaging team leader, Bradford Smith, approved a single exposure, essentially as a courtesy, for completeness. One frame, Owen is the first author on the discovery paper. The ring is extraordinarily faint, and the numbers are worth stating because faint is not a strong enough word. Jupiter's main ring has an optical depth of a few parts in a million. It blocks essentially none of the light that passes through it. If it were a pane of glass, you would not be able to tell whether it was there. Its total mass, in the grain sizes that scatter light, is somewhere between 10 million and a billion kilograms. 10 million kilograms is the mass of a large ship, spread out around a planet whose circumference is nearly 500,000 kilometers. The follow-up observation is what identified what the ring is made of, and it is a clever piece of work. On the 10th of July 1979, Voyager 2 photographed the ring from inside Jupiter's shadow, looking back toward the Sun. In that geometry, the ring lit up dramatically, far brighter than it had appeared from the sunward side. That is diagnostic. Particles around a micrometer across scatter light strongly forward and weakly backward, much the way dust on a windscreen is invisible until you drive toward a low sun. The brightness ratio gave the grain size directly. Jupiter's ring is not ice, and it is not rock. It is dust. Dark, reddish, non-icy grains of silicate and carbon, dominated by particles around 15 micrometers across, with a reflectivity comparable to charcoal. It was the first dusty ring ever identified from space. Where the dust comes from is the part that makes this entry belong on the list. The main ring is fed by micrometeoroid impacts on two small inner moons, Metis, orbiting at 127,978 kilometers, and Adrastea at 128,980, sitting right at the ring's outer edge. Farther out, two much fainter rings, called the Gossamer rings, are fed the same way by the moons Amalthea and Thebe. Each Gossamer ring extends inward from its source moon and ends precisely at that moon's orbit, which is about as clear a fingerprint of origin as planetary science ever gets. Interior to the main ring is a halo, a vertically thick torus of grains, lifted 10,000 kilometers out of the ring plane by Jupiter's magnetic field rather than by gravity. And here is the thing to sit with. Jupiter's ring cannot be a leftover from the formation of the solar system. It is not possible. Grains that small are removed by radiation pressure and drag within a few thousand years at most. Every particle in that ring was blasted off a moon recently, in astronomical terms, and will be gone soon. The ring is a continuous fine spray of pulverized moon, replenished at exactly the rate it is destroyed. It is not a structure. It is a process, caught in the act, and it happens to have been caught by an 11-minute exposure that almost nobody wanted to take. A few more figures fill it in. The Discovery exposure was taken from 1,212,000 kilometers away, with the ring's outer edge about 57,000 kilometers above Jupiter's cloud deck. The main ring is under 30 kilometers thick. That is a sheet 129,000 kilometers in radius, and thinner than the height of a mountain range. Adrastea, meanwhile, is one of the fastest orbiting moons known anywhere, circling Jupiter in about 7 hours, which is faster than Jupiter itself rotates. All 4 giant planets are now known to have rings. Before 1979, only Saturns were considered certain, and Uranuses had been detected 2 years earlier by an accident of timing that we will come to. There is a detail in the geometry of that discovery frame that deserves attention. Voyager 1 was very nearly in the ring plane when it took the exposure, looking edge-on through the entire width of the ring at once. That is the only reason there was enough material along the line of sight to register at all. A few degrees off, and the 11-minute exposure would have returned exactly what everyone expected it to return, which is nothing, and the ring would have waited for another spacecraft. The reason the ring is dark rather than bright like Saturn's comes down to what it is made of. Saturn's rings are water ice, which is one of the most reflective materials in the solar system. Jupiter's ring is silicate and carbon dust knocked off small, dark, rocky moons. The same process, running on different raw material, produces a structure that is essentially invisible instead of one that can be seen through a garden telescope. Two ring systems around two neighboring planets, separated by nothing more fundamental than the composition of the moons that feed them. The halo is worth one more sentence, because it is the strangest component. It reaches roughly 10,000 kilometers above and below the ring plane, which makes it more of a donut than a disk, and it is held in that shape electromagnetically. Grains at the inner edge of the main ring pick up an electric charge, and Jupiter's magnetic field, which is tilted relative to the rotation axis, then flings them out of the plane. Gravity is not in charge of that structure at all. One correction, since it circulates. The splitting of the Gossamer ring into two separate components, one from Amalthea and one from Thebe, was a Galileo result in 1999. Voyager found the Gossamer material on reanalysis in 1985, but not its structure. That exposure was aimed at empty space. The next thing Voyager pointed at was the most famous feature on any planet, and nobody had ever seen it move. Number 14. The storm we finally watched turn. Between the 6th of January and the 3rd of February 1979, on its long approach to Jupiter, Voyager 1 took 66 images of the planet through a blue filter. One image per Jupiter rotation, which is one every 9 hours and 55 minutes, as the range closed from 58 million kilometers down to 31 million. Each frame had to be individually navigated and reprojected before it could be used. Assembled in sequence, those 66 frames became the first time-lapse film of another planet's weather. It is difficult now to appreciate what that changed, because the footage has been reproduced so many times that it has become wallpaper. But before that sequence existed, the Great Red Spot was a mark on a disk. It was a feature in a drawing, then a feature in a photograph, then a feature in a series of photographs taken years apart. After the sequence, it was a machine, and everyone could see what kind of machine it was. The spot rotates counterclockwise, which in the southern hemisphere makes it anticyclonic, a high-pressure system rather than a low-pressure one. The circulation period at its outer edge is roughly 6 to 7 days, depending on which part of the structure is being tracked. Every source that gives a shorter figure than that should be treated with suspicion. The bands to the north and south of it move in opposite directions. The spot sits wedged between them, turning, the way a ball bearing turns when it is held between two belts running opposite ways. That is what the film showed, and it is what explains the spot's longevity better than anything else. It is not a storm sitting in a wind. It is a storm being driven by two winds. Smaller white ovals were seen drifting into it and being pulled apart. Material entering on one side was tracked leaving on the other. The spot is not a sealed vessel. It is continuously exchanging material with the atmosphere around it and continuously eating the smaller storms that come too close. The size needs stating carefully because the figure in general circulation is wrong. In 1979, the Great Red Spot measured about 23,335 kilometers along its long axis. The Earth is 12,742 kilometers across. So the spot was about 1.8 Earth diameters wide. It was not 2 to 3 Earths. The 3 Earths figure belongs to measurements made in the late 1800s, when the spot spanned something like 41,000 kilometers and could genuinely have swallowed 3 of our planets in a row. By 2014, it had shrunk to about 16,350 kilometers, roughly 1.3 Earths. Since 2012, it has been contracting at something in the region of 900 kilometers a year, which means Voyager did not photograph a permanent feature. It photographed a storm halfway through a long, continuous decline that had already been running for a century when the cameras arrived, and has continued at an accelerating rate since. The winds Voyager measured around the spot's rim ran at roughly 400 to 435 kilometers per hour. That is comparable to a strong jet stream on Earth, except that a terrestrial jet stream is a seasonal river of air, and this is a closed circulation that has been sustaining those speeds for at least 2 centuries without interruption. Hubble measurements taken between 2009 and 2020 put the outer ring winds above 640 kilometers per hour, an increase of about 8%, occurring while the storm itself was shrinking. A smaller storm turning faster is exactly what conservation of angular momentum predicts, and it is a little unsettling to watch it happen on a planetary scale in real time. Then there is the question that the time-lapse made unavoidable. Why does it not stop? On Earth, a hurricane dies for 2 reasons. It moves over land or cold water and loses the warm ocean that feeds it, and it drags against the surface and loses energy to friction. Jupiter offers neither of those. There is no land anywhere beneath the spot. There is no ocean surface, no coastline, no continent, nothing to run aground on. The atmosphere simply gets denser with depth until the hydrogen stops behaving like a gas and starts behaving like a liquid, and then, deeper still, like a metal. At no point is there a boundary the storm could break against. Juno's later measurements, using gravity and microwave sounding, established that the spot extends at least 200 to 300 kilometers downward and possibly considerably further. That reframes it entirely. It is not a weather system sitting on top of a planet. It is a structure rooted into one, with a depth comparable to the entire vertical extent of Earth's atmosphere several times over. The 2 Voyagers also produced between them the first proper survey of Jupiter's zonal jets. The alternating bands and zones that had been sketched by observers for 3 centuries were resolved into a system of high-speed currents with measurable velocities, and the turbulence between them turned out to be far more energetic and far more organized than anything the Earth-based record had suggested. When Voyager 2 arrived 4 months after its twin, in July of 1979, the surroundings of the spot had visibly changed. The atmosphere was being rearranged on the timescale of a season, not a century. And there are 2 things about the Great Red Spot that nobody can answer, both of which have been open for as long as the questions have been asked. The first is why it is red. The leading idea involves compounds produced when ultraviolet sunlight breaks down ammonia and acetylene in the upper reaches of the storm, where the circulation lifts material higher than anywhere else on the planet. Laboratory work has produced reddish products by roughly that route. But the chemistry has never been pinned down, and the color varies over decades in ways no model predicts. There have been periods in the 20th century when the spot was barely colored at all. The second is how old it is. Giovanni Cassini, the same man who lost Iapetus, recorded a permanent spot on Jupiter in 1665, and it was observed for several decades afterward. Then the record goes quiet for well over a century. The modern spot was described in 1831. Whether Cassini's spot and the modern spot are the same storm, or 2 different storms in the same latitude band, has never been settled, and probably cannot be. So the situation is this: a structure large enough to contain the Earth, turning continuously in an atmosphere with no floor, driven by 2 opposing jets, eating smaller storms, rooted hundreds of kilometers deep, of unknown age, of unexplained color, and measurably dying. Voyager filmed it. The film is the reason we know how it works, and the film is also the reason we can see how much it has changed since. The generation alive when those 66 frames were assembled is the first generation to watch the Great Red Spot move. Depending on how the shrinkage continues, it may also be among the last to see it as a red spot at all. That storm has been turning since before anyone alive was born. The next entry is a place where the ground itself looks as though it was assembled out of mismatched parts. Number 13. The cliff you would fall from for minutes. On the 24th of January 1986, about an hour before its closest approach to Uranus, Voyager 2 passed within roughly 29,000 kilometers of a small moon called Miranda. That was the closest the spacecraft had come to any body in 8.5 years of flight. Nobody expected much from it. Miranda is the innermost of the 5 major Uranian moons and the smallest, with a mean diameter of about 472 kilometers. It had been discovered by Gerard Kuiper on the 16th of February 1948 at the McDonald Observatory in Texas, and for 38 years it had been a point of light. The reasonable expectation was a cold, cratered, geologically dead ball of ice, because that is what small icy moons at that distance from the Sun are supposed to be. It received a close pass largely because of where it happened to sit in the trajectory. It turned out to be the strangest surface the entire mission ever photographed. The images show a collage. Ancient, heavily cratered terrain of the kind everyone predicted sits directly against enormous oval and trapezoidal regions filled with grooved, banded, concentric ridges, and the boundaries between the two kinds of ground are sharp. Not gradual. Sharp enough that you could stand with one foot in terrain billions of years old, and the other in terrain that has been resurfaced. 3 of those regions are large enough to be named. Elsinore is the largest, about 323 kilometers across, on the trailing side. Arden is about 318 kilometers on the leading side. Inverness is about 234 kilometers, near the South Pole, and its bright chevron shape is the feature most people would recognize if shown a picture of Miranda without being told what it was. They are called coronae, a term borrowed from the geology of Venus, and it is worth saying plainly that the borrowing does not imply the same process. Nothing else in the solar system looks like them. And on the edge of Elsinore there is a cliff. Verona Rupes is generally described as the tallest cliff face known anywhere in the solar system, and that description is defensible. It needs to be stated carefully, though, because the number attached to it in popular sources is the least supported one available. There is no official height. The United States Geological Survey Gazetteer lists Verona Rupes with a diameter of 116 kilometers, and that figure is the extent of the feature on a map, not its vertical drop. The peer-reviewed estimates run from 5 to 10 kilometers in one analysis and 5 to 15 in another. NASA's own outreach material says about 10 kilometers in one place and about 20 in another. The 20-kilometer figure is the upper bound of the range, and it is the one that gets quoted because it is the most impressive. The honest statement is that Verona Rupes is somewhere between about 5 and 20 kilometers high, with most published estimates nearer 10. Even at the low end, it is taller than any cliff on Earth by a factor of several. The tallest sheer drop on our planet, depending on how you measure it, is something in the region of 1.25 kilometers. Now the part that makes this entry worth its place, which is not the height. Miranda's surface gravity is 0.079 meters per second squared. Earth's is 9.81. So gravity on Miranda is about 124th of what you are experiencing right now. Step off the top of Verona Rupes, and you do not plummet. You drift. From a 5-kilometer drop, the fall takes about 6 minutes. From 10 kilometers, about 8.5. From 15, about 10. From the 20-kilometer upper bound, about 12 minutes, arriving at roughly 200 kilometers per hour. NASA's own materials quote 8 minutes in one place, 10 in another, and 12 in a third, and the reason for the inconsistency is not carelessness. It is that the height is genuinely unknown, and each figure is correct for a different assumed height. So the honest version, the one to hold on to, is that falling from the tallest cliff in the solar system takes somewhere between about 8 and 12 minutes. Not 8 seconds. 8 minutes. Consider standing on the rim. The ground underfoot is water ice at around 60 Kelvin, which is minus 213 Celsius, cold enough that ice has the mechanical properties of granite. It is bright, and it is hard, and it does not give at all. There is no atmosphere, and therefore no sound, and no wind. Uranus hangs in the sky as a pale blue-green disk, very large, and lit strangely because the whole system is tipped over on its side, and the sunlight is arriving almost along the axis. The horizon is close, only a few kilometers away, because the entire world is smaller than England. Below the edge, the drop goes down further than any drop on Earth by a wide margin. And the danger is not speed. The danger is time. You would fall for 8, 10, perhaps 12 minutes, watching the wall of ice slide past at first at walking pace, and then gradually faster, with more than enough opportunity to consider the situation from every angle. And behind you, running across the ground, is the line where the terrain changes character completely, one kind of surface on one side and another kind on the other, and no one has ever explained what put it there. That is the real question about Miranda. Not the cliff, the collage. The old and popular explanation, and the one still on NASA's public page, is that Miranda was shattered by a massive impact and then reassembled from its own fragments under its own gravity, leaving the interior exposed in patches. It is a memorable story, and it is now disfavored in the literature. The current consensus is internal rather than catastrophic. Buoyant plumes of warmer, lower-density ice rose slowly through the Moon, driven by tidal heating during a past orbital resonance, and resurfaced the regions above them while leaving the terrain between them untouched. The technical term is diapirism, and it is the same broad process that produces salt domes in Earth's crust, operating on ice over hundreds of millions of years. The heating source was almost certainly a 3-to-1 resonance with the Moon umbriel, which would have pumped up Miranda's orbital eccentricity, flexed it, and warmed it. Miranda's orbit is nearly circular now, so whatever drove the resurfacing has long since switched off. In October of 2024, a stress analysis of the surface patterns pushed this further. The distribution of the fractures implies a subsurface ocean at least 100 kilometers deep beneath a crust no thicker than 30, present somewhere between 100 and 500 million years ago. On a moon 472 kilometers across, an ocean 100 kilometers deep is not a feature of the Moon. It is most of the Moon. And then there is the fact that makes Miranda genuinely uncomfortable to think about. Voyager 2 saw it for a few hours. It photographed roughly 40% of the surface at useful resolution, and essentially all of that was the southern hemisphere, because the extreme tilt of the Uranian system meant the sun was almost directly over the South Pole, and the entire northern half of every moon in the system was in darkness. The northern hemisphere of Miranda has never been photographed by anything. Not by Voyager, not by any telescope, not by any spacecraft since. It is a blank. The tallest cliff in the solar system was found in a 6-hour flyby by a spacecraft that was never designed to go there, on a moon whose far side no human being has ever seen, and there is no approved mission to go back and look. 2 more details fill the picture in, and both are the kind of thing that only becomes visible when you look at the whole encounter rather than the single image. The first is that the Uranus close approach science phase, the part where the instruments were gathering data at useful resolution on anything, lasted under 6 hours from beginning to end. 8.5 years of flight, a spacecraft launched when the people running the encounter were young, and the entire close-range harvest for a planet and 5 major moons was collected in less time than a working day. The second is about the geometry of that harvest. Because Uranus is tipped over, Voyager 2 did not fly past the system the way it had flown past Jupiter and Saturn, sweeping through a plane of orbiting moons like a car passing a roundabout. It came in almost along the axis, like a dart at a dartboard. That meant one pass at each moon, at whatever distance the geometry happened to allow, with no opportunity for a second look at anything, and with the sun fixed over the South Pole so that half of every body was in permanent darkness. Every close-up image of every Uranian moon in every textbook comes from that arrangement. It is not a representative survey. It is a single dart, thrown once, at a board that was turned side-on. And Verona Rupes itself is not, strictly speaking, a vertical wall. It is a very steep scarp, and the fall times quoted assume free fall rather than a slide down a slope. Whether you would fall clear of the face for the whole 8 to 12 minutes, or bounce and slide, depends on details of the local topography that were never resolved. Nobody has photographed it at high enough resolution to say, Miranda is a moon of Uranus. And Uranus is the strangest planet Voyager visited, and the only one that has ever been visited at all. Number 12, the planet lying on its side with a broken magnetic field. Voyager 2 reached Uranus on the 24th of January 1986 at about 5:59 in the evening, Universal Time, passing roughly 81,500 kilometers above the cloud tops. It remains the only spacecraft ever to visit the planet, and it is worth being blunt about what that means. Everything humanity directly knows about Uranus from close range comes from a single pass, lasting a few hours 40 years ago, by a spacecraft designed in the early 1970s. Start with the tilt, because everything else follows from it. Uranus's axis is inclined 97.77 degrees. It does not spin upright like Earth, and it does not spin at a lean like Saturn. It spins on its side, rolling along its orbit like a barrel. Nobody knows why with any certainty. The usual explanation is one or more enormous collisions early in the planet's history, though the details have never worked cleanly, and more recent work has explored whether a large former moon could have tipped the planet over gradually instead. The consequence is the most extreme seasonal cycle of any planet in the solar system. Each pole spends 42 years in continuous sunlight, and then 42 years in continuous darkness. Not a long summer. A summer that lasts longer than most human careers, followed by a night of the same length. When Voyager arrived, the South Pole was pointed almost directly at the Sun. That is the geometry that shaped the entire encounter and left half of every moon unphotographed. Then there is what the planet itself looked like, which is almost nothing. Voyager's images of Uranus show a pale, featureless blue-green disk. The imaging team stretched the contrast severely, well past the point where the noise becomes visible, and recovered a handful of faint clouds from which the atmospheric rotation could barely be derived at all. It is the least visually informative planetary encounter of the entire mission, and it was the first sign that Uranus is genuinely different rather than merely distant. The reason it is blank is that Uranus radiates almost no internal heat. Every other giant planet in the solar system gives off substantially more energy than it receives from the Sun, and that internal heat stirs the atmosphere from below and drives the visible weather. Uranus does not. Its atmosphere is not being convected from underneath, so there is very little to see. Its cloud top temperature, about 49 Kelvin, is the coldest measured atmosphere of any planet, colder than Neptune's, despite Uranus being 1.5 billion kilometers closer to the Sun. But the real anomaly at Uranus was not visual. It was magnetic, and Voyager's magnetometer found it in a few hours. Earth's magnetic field is tilted about 11 degrees from its rotation axis, and it is roughly centered on the planet. Uranus's field is tilted 59 degrees. And, far stranger, It is offset from the planet's center by roughly a third of the planet's radius, displaced toward the southern hemisphere. It is not a bar magnet through the middle. It is a bar magnet shoved off to one side and tipped over. The practical consequence is that the field strength at the cloud tops varies by about a factor of 10 between one hemisphere and the other, which is a difference no other planet comes close to. That geometry rules out the kind of dynamo Earth has. A field that badly aligned cannot be generated in a deep, well-organized, convecting metallic core. The current picture is a dynamo operating in a relatively thin and unstable shell of electrically conducting ionic fluid, water and ammonia and methane, compressed to the point where they conduct, somewhere in the planet's mantle rather than at its center. Whatever is going on inside Uranus is not organized the way the inside of any other giant is organized. And because the planet is lying on its side while all this is happening, the magnetotail, the long streamer of field dragged out behind the planet by the solar wind, is twisted into a corkscrew. NASA's own description uses that word. The helix has a pitch of a few degrees, and the tail has been traced for something like 10 million kilometers. For all that, the encounter was productive. In a single pass, Voyager 2 discovered 10 new moons, bringing the known total to 15, and 2 new rings, bringing that count to 11. An 11th moon, Perdita, was sitting in the 1986 images the whole time and was not identified until 1999, dismissed in 2001, and finally confirmed by the Hubble Space Telescope in 2003. 13 years to find a moon in a photograph that had already been taken. The rings themselves had not been found by imaging at all. They were discovered by accident on the 10th of March 1977, when astronomers watching Uranus pass in front of a star saw the star blink several times before the planet reached it, and several times again after it passed. That is the signature of narrow rings. They are among the darkest objects in the solar system, reflecting about as much light as charcoal. Voyager also pinned down the planet's rotation, using its radio emissions and magnetometer data at 17 hours, 14 minutes and 24 seconds. That figure defined the Uranian coordinate system for 4 decades. In April of 2025, it was revised, using more than a decade of Hubble ultraviolet auroral tracking, to 17 hours, 14 minutes and 52 seconds. 28 seconds longer, and about 1,000 times more precise. And then there is the twist that arrived in November of 2024, which reframes the whole encounter. A reanalysis of the 1986 magnetometer data established that Voyager 2 happened to arrive during an unusual compression of the solar wind, a condition present less than 5% of the time. The magnetosphere had been squashed to roughly a fifth of its normal volume and emptied of plasma. The strange radiation belts, the peculiarly empty magnetosphere, the features that have sat in textbooks for 40 years as the defining characteristics of Uranus, may well be transient weather rather than the planet's normal state. A few days earlier or a few days later, and the spacecraft would have measured something substantially different. The one visit anyone has ever made to Uranus caught the planet on an unrepresentative afternoon, and there is no way to check. That is the thing to hold on to here. Every close-up photograph of a planet 4 times the width of Earth, every measurement of its field, every image of its moons, comes from 6 hours in January of 1986. These are the only photographs that exist. There is no mission approved to take more. 2 footnotes belong here, because both are frequently repeated and both need correcting. The first is a term that came out of Voyager's ultraviolet data and then quietly died. The spectrometer found more ultraviolet emission from Uranus's day side than the models could account for, and the team gave the excess a name: electroglow. For a short period, it was treated as a genuine mystery, a novel process operating in the upper atmosphere of an ice giant. Within about a year, the idea had largely been dismantled. Ordinary scattering by molecular hydrogen, combined with excitation by photoelectrons, accounts for the emission perfectly well, and the brightness turned out to track the solar flux, which is exactly what a mundane explanation predicts. Electroglow is a superseded term, not an open question, and it still appears in secondary sources as though it were the latter. The second is more satisfying. In March of 2020, someone went back through the raw magnetometer data from the 1986 flyby and found a plasmoid in it. A plasmoid is a bubble of a planet's own atmosphere, pinched off by the magnetic field and carried away down the magnetotail into space. It had been sitting in the data for 34 years, in a 50-second stretch of readings, unremarked. Uranus is losing its atmosphere in packets, and the evidence had already been collected and stored before anyone thought to look for it. That is the recurring shape of the Voyager archive. The spacecraft collected far more than anyone could analyze at the time, and it continues to yield results, decades later, to people who were not born when it was taken. Voyager saw almost nothing at Uranus. At Jupiter, 7 years earlier, it had already seen something in almost total darkness. Number 11. Lightning on a world with no ground. On the 5th of March 1979, about 6 hours after its closest approach to Jupiter, Voyager 1 passed into the planet's shadow, turned its wide-angle camera back toward the night side, and held the shutter open for 3 minutes and 12 seconds from a range of roughly 515,000 kilometers. The resulting frame is one of the strangest images in the entire mission archive, and it is strange partly because it is so nearly empty. It is almost entirely black. Scattered across the darkness, there is a handful of bright points. And along the limb, near the North Pole, there is a long, bright double streak. The points were lightning. The streak was an aurora. Neither had ever been photographed on another world. The priority claim needs stating honestly, because it is often overstated. Voyager 1 returned the first photographs of lightning on another planet, and the first unambiguous detection of it. It was not the first detection of any kind. Venera 11 and 12 had recorded very low-frequency radio pulses at Venus in December of 1978, and Pioneer Venus found Whistler-like signals in the same month, roughly 3 months earlier. Venus's lightning remains disputed to this day, because later missions looking for optical evidence found none. So the accurate framing is that Voyager took the first pictures. The energy figures need the same care. The flashes Voyager measured came in at around 1 billion joules each, with a range running from about 200 million to 16 billion. NASA's own caption for the image describes them as comparable to terrestrial superbolts. That is the correct comparison, and it is a strong one. Superbolts are the rarest and most powerful class of lightning on Earth, occurring in roughly 1 strike in 10 million. Voyager's typical Jovian flash was in that class. The figures circulating that put Jovian lightning at 10,000 or 1 million times terrestrial lightning are drawn from much later analysis of Juno data, not from Voyager, and should not be attached to this image. There was a second detection running in parallel on a completely different instrument. Voyager's plasma wave instrument picked up whistlers. A whistler is a radio signal produced by a lightning stroke that travels along a magnetic field line and arrives smeared out in frequency, so that the higher frequencies get there first and the pitch appears to slide downward. They were first identified on Earth in the early days of long-distance telephony, when operators heard descending tones after distant storms and had no idea what they were listening to. Voyager recorded 167 of them, all on the 5th of March 1979. 90 had measurable dispersion, which is what allows the path length to be calculated, and they were not found near Jupiter's poles. They were found out in the Io plasma torus, at 5 to 6 Jupiter radii, and at peak 32 arrived within a single 48-second frame. About 1 per second. The instrument's principal investigator was Frederick Scarf. Donald Gurnett, of the University of Iowa, built the instrument and led the lightning analysis. Gurnett's name will come back later on this list, in a considerably more dramatic context, about 34 years further on. What makes lightning on Jupiter genuinely strange is not its power. It is where it has to go. Terrestrial lightning is generated by collisions between ice and water in clouds, and Jupiter has water clouds too, deep down, at a level where the pressure is several bars. Voyager's flashes came from that depth. That is why they look like soft, diffuse glows rather than sharp forks. The light had to scatter its way upward through hundreds of kilometers of overlying cloud before it could escape, and by the time it reached the camera, all the structure had been smeared out. But on Earth, the majority of the energy in a thunderstorm eventually finds the ground. That is what lightning is for, in the crude sense. It is a discharge between a charged cloud and a surface. Jupiter has no surface. There is nowhere for the charge to go. Every discharge is cloud to cloud, in an atmosphere with no bottom to it, in a weather system that has no coastline to weaken it and no continent to break against. The charge separates, builds, discharges, and the whole cycle runs again, and it has been running that way for longer than the Earth has had an atmosphere. The aurora on the limb runs on a different principle from Earth's as well. Earth's aurorae are driven mostly by the solar wind. When the sun is quiet, the aurorae are quiet. Jupiter's are driven mostly by Jupiter itself, by the enormous rotational energy of a planet turning once every 9 hours and 55 minutes, and by material fed continuously into its magnetosphere from the moon Io. It is the most powerful aurora in the solar system. It is visible in ultraviolet and in X-rays as well as in visible light, and it does not need the sun to have a bad day. It simply runs. The auroral ovals also carry bright spots that are the magnetic footprints of individual moons. Io, Europa, and Ganymede each leave a mark in Jupiter's upper atmosphere that moves as they move. The planet's northern lights carry a set of moving labels identifying its own moons. One number attached to this image should be discarded. The figure of a 30,000-kilometer aurora circulates widely, and it is a misreading. That number is the length of Jupiter's visible limb in the frame, not the length of the auroral arc. NASA describes a long, bright double streak near the North Pole and gives no length at all. What Voyager did here is worth appreciating as an act of nerve. It pointed a camera at a planet that filled a large part of the sky and was almost entirely dark, held the shutter open for over 3 minutes, and spent an imaging slot on a frame that might well have come back as a black rectangle. Later missions filled the picture inconsiderably, and each one raised the numbers. Galileo detected Jovian lightning in 1998. Cassini saw it in visible light in 2000, on its way past to Saturn. Juno, arriving in 2016 and flying far closer to the poles than anything before it, recorded rapid sequences of whistlers peaking at 4 flashes per second, which is 6 times Voyager's peak rate, and detected hundreds of radio signatures at 600 megahertz that had never been accessible before. Juno also found something in 2020 that nobody had anticipated: shallow lightning. Discharges occurring high in the atmosphere, well above the water cloud layer, in a solution of ammonia and water that stays liquid at temperatures far below the freezing point of pure water. On Jupiter, ammonia acts as antifreeze, and the result is a second, entirely separate lightning system operating in a temperature regime where terrestrial physics says there should be nothing but ice. So Jupiter has at least 2 kinds of lightning, running at different altitudes, powered by different chemistry, in an atmosphere with no flaw, discharging into itself forever. and the whole line of investigation began with a single 3-minute exposure of a dark planet, taken because someone was willing to gamble an imaging slot on it. Jupiter's magnetosphere, the structure inside which all of this happens, is the largest single object in the solar system after the heliosphere itself. If it emitted visible light, it would appear from Earth several times wider than the full moon. The lightning was a discharge lasting a fraction of a second. The next entry is a circuit that has never once switched off. Number 10. The circuit running between a planet and its moon. Io orbits Jupiter deep inside that magnetosphere, and it moves relative to the magnetic field lines sweeping past it at about 17 kilometers per second. That single fact sets up one of the strangest permanent structures in the solar system. Any conductor moving through a magnetic field generates a voltage across itself. That is the principle every electrical generator on Earth runs on. Io qualifies as a conductor. It has a thin ionosphere, and it is continuously shedding ionized gas from its volcanoes. So Io generates a voltage, and the voltage is about 400,000 volts across the moon's diameter. That potential drives a current. The current runs along the magnetic field lines that connect Io to Jupiter's polar regions in both hemispheres at once, so the circuit is closed through the planet and back through the moon. Voyager 1's magnetometer measured it at about 2.8 million amperes. The figure worth using is about 3 million amps. The 5 million figure appears in older popular sources and is not the measured value. 3 million amperes is difficult to picture, so here is a comparison. A large lightning strike on Earth carries something in the region of 30,000 amps for a few tens of microseconds. The Io flux tube carries 100 times that current, continuously, without interruption, and has done for as long as Io has been in that orbit. The power involved is on the order of a terawatt, which is roughly comparable to the entire electrical generating capacity of the human species, running without a break. There is no switch. There is no off state. There is a moon and a planet wired together across 420,000 kilometers of vacuum, and the wire is made of magnetic field. The material in that circuit comes from Io itself, and the quantity is substantial. Io loses about a ton of material every second, mostly sulfur dioxide, which is broken apart into sulfur and oxygen. Roughly 30% of it becomes ionized and is captured by Jupiter's magnetic field, where it is swept up and spun around the planet. The result is a donut of charged gas encircling Jupiter along Io's orbit. It is called the Io plasma torus, and Voyager 1's ultraviolet spectrometer and plasma instruments mapped it from the inside in 1979. Credit needs to be assigned honestly here, because Voyager is often given the discovery and did not make it. A cloud of sodium around Io was found from the ground in 1974. Ionized sulfur in the torus was detected spectroscopically in 1976, 3 years before the flyby, by watching the emission lines of sulfur ions. What Voyager contributed was the in situ measurement, flying through the structure and characterizing it directly, rather than inferring it from a distance. The temperatures in the torus are worth stating carefully, because a single number is misleading. The ions sit at roughly 1,000,000 Kelvin. The electrons are far cooler, around 50 to 60,000. So the torus is hot in the sense that its particles move extremely fast, and it is thin in the sense that there is almost nothing there. Those two facts sitting together, high temperature and negligible heat, will return much later on this list in a considerably more famous form, and it is worth noticing the pattern now. The torus does two things that matter for the whole Jovian system. The first is that it is the reason Jupiter's aurora is powered from within. Earth's magnetosphere is fed almost entirely by the solar wind. Jupiter's is fed by a moon at a ton per second, and the planet's rotation flings that material outward and accelerates it, and the resulting current systems dump energy into the polar atmosphere continuously. The second is that the torus is one of the most intensely irradiated regions in the solar system. Voyager 1 passed through it and took a measurable dose. The spacecraft's clock ran slow for a period afterward, and several instruments returned degraded data for a while. Any future mission that wants to spend serious time near Io has to be engineered around that environment, which is a significant part of why no mission has yet gone to orbit the most volcanically active body in the solar system. An unshielded human standing on Io would receive a lethal radiation dose in under an hour, and the radiation would not be coming from Io. It would be coming from the field the moon is embedded in. Finally, the circuit does not just flow. It lands. Where the Io flux tube meets Jupiter's upper atmosphere, it deposits its energy and produces a bright, ultraviolet spot in the aurora. That spot moves as Io moves, completing a circuit of the polar region every 42.5 hours, which is Io's orbital period. Europa and Ganymede produce their own fainter footprints. The Jovian system is running several of these circuits simultaneously, and the planet's aurora carries a live map of where its major moons currently are. The plasma in the torus, meanwhile, is spun up by Jupiter's rotation to speeds well above Io's own orbital speed, which means Io experiences it as a constant wind blowing past, stripping more material away, feeding the torus further. It is worth staying with the numbers for a moment longer, because the flux tube is one of those structures where every figure sounds like an exaggeration, and none of them are. 400,000 volts is roughly the potential of a long-distance electricity transmission line, the kind carried on the largest pylons. 3 million amperes is a current no terrestrial engineering has ever produced continuously by any means. Put together, they give a power of over a terawatt, and that power is being delivered along a pair of magnetic field lines that are, in every physical sense, empty space. There is no cable. There is nothing there to see. If you flew a spacecraft through the flux tube, and Voyager 1 effectively did, you would pass through what looks like vacuum while a current larger than any human machine has generated flows around you. The torus is also visible from Earth, which is how it was found in the first place. Ionized sulfur and oxygen emit at specific wavelengths, and the torus has been monitored from the ground for decades. It brightens and dims as Io's volcanic output rises and falls, which means that from a telescope on Earth, it is possible to watch a moon 500 million kilometers away change its eruption rate indirectly by watching a ring of gas around a different body glow more or less brightly. Radio emission from the Jupiter and Io system was picked up from Earth back in the 1960s. Observers found that Jupiter's radio output was being modulated by the position of one of its moons, and nobody could account for why a moon should have any influence at all on a planet's radio emission at that distance. The flux tube is the answer, and it took a spacecraft flying through the system to supply it. And every part of this arrangement is a consequence of Io's orbit rather than anything about Io itself. Move the same moon out to Callisto's distance and none of it happens. The voltage collapses, the torus disappears, the aurora dims, the radiation environment relaxes, and the moon stops being resurfaced. Io's entire character, including everything in the next entry, is a product of where it is rather than what it is. All of that is a side effect. The energy dissipated in the flux tube is a small fraction of the energy being dissipated inside Io itself, and the thing producing it is the most violent world in the solar system. It was found by someone whose job that day was to look past it. Number 9. The world that is melting itself alive. On the 8th of March 1979, at 28 minutes past 1 in the afternoon, Greenwich time, 3 days after Voyager 1's closest approach to Jupiter, The spacecraft took a long exposure of Io from a range of about 4.5 million kilometers. The image was not taken for science. It was taken for navigation. Optical navigation works by photographing a body whose position is known against background stars whose positions are known extremely precisely, and then solving for where the camera must have been. For that to work, the stars have to be visible, and the stars in question were faint, catalogued as AGK3 2006 and AGK3 10021 at magnitudes 7.2 and 8.3. So the exposure was deliberately long, which meant Io itself was massively overexposed and blown out into a featureless crescent. The moon was, in the most literal sense, the thing the photograph was designed to ignore. The following day, on the 9th of March, the engineer responsible for processing those navigation frames brought this one up and enhanced it to bring out the faint stars. Her name was Linda Morabito, and she was the cognizant engineer for the optical navigation image processing system on the Voyager navigation team. Off the edge of Io's disk, projecting about 1/1500ths of an Io radius beyond the limb, there was a mushroom-shaped cloud. Her first thought was that it was another moon, sitting behind Io in the frame. She checked the geometry, and there was no moon that could be there. Her second thought was that it was an imaging artifact, which is what most anomalies in most images turn out to be, and which is the point at which most people would have moved on to the next frame. And this is the detail that makes the story worth telling properly. The cloud was crescent-lit. It was brighter on the side facing the sun and darker on the side away from it. Artifacts are not illuminated. Scattered light, dust on optics, electronic noise, none of them have a sunward side. Whatever this was, it was a three-dimensional object, hanging above the surface of Io, catching sunlight from the same direction as the moon underneath it. It was a volcanic plume. It was later identified as Pele, and in the same frame, at the terminator, projecting above the dark side of the moon into sunlight, there was a second one, from a volcano now called Loki, which was noticed shortly afterward. Linda Morabito was the first human being to see active volcanism on a world other than Earth. She saw it in a housekeeping image, taken for a purpose that had nothing to do with Io, by a spacecraft that had already passed the planet. And she saw it because when a routine frame contained something that looked like an artifact, she took the trouble to work out why an artifact would have a lit side. The plume's height is disputed in the way that most of the best Voyager numbers are disputed. Morabito's own estimate was about 250 kilometers. NASA's caption says more than 260. Secondary sources say 270. The general literature figure for Pele runs closer to 300. Somewhere between 250 and 300 kilometers is the honest answer, and any of those numbers is difficult to hold in the head, so here is a comparison. It is roughly 30 times the height of Mount Everest, thrown up silently by a moon smaller than Mars. There is one more piece of timing that makes this the best week in the history of planetary science. On the 2nd of March 1979, 6 days before the Discovery image was taken, and 3 days before Voyager 1 even reached its closest approach to Jupiter, a paper appeared in the journal Science under the title Melting of Io by Tidal Dissipation. It was written by Stanton Peele, Patrick Casson, and Ray Reynolds. It argued that Io, caught in an orbital resonance with Europa and Ganymede that prevents its orbit from becoming circular, would be flexed by Jupiter's gravity hard enough to heat its interior, and that widespread melting and surface volcanism were the likely result. Published on the 2nd, Flyby on the 5th, Discovery image on the 8th, Discovery on the 9th. It is one of the most precisely timed predictions anyone has ever made, and it was confirmed within a week of appearing in print, by a photograph that was not looking for it. What Io actually turned out to be is worth laying out in full. It is roughly the size of Earth's moon, 3,640 kilometers across, and it is the most volcanically active body in the solar system by an enormous margin. About 400 volcanic centers have been identified on its surface. Something like 150 are erupting at any given moment. Loki Patera, the largest of them, is a lava lake 202 kilometers across. That is the largest volcanic depression known anywhere. It accounts on its own for something like 1/10 of the entire Moon's heat output. The average surface temperature is about 130 Kelvin, which is minus 143 Celsius. The hotspots exceed 1500 Kelvin. Lava temperatures around 1600 Kelvin are the defensible figure, and some earlier analyses suggested higher, which would imply exotic compositions not seen on Earth since the very early solar system. That remains unsettled. The colors are sulfur chemistry. Yellow, white, orange, red and black, all of them compounds of sulfur and sulfur dioxide at different temperatures and in different states, and the reds are the freshest deposits. Io looks, in true color, like something that has gone badly wrong in a laboratory. But the single most telling feature of Io is not something present. It is something absent. Io has no impact craters. Not a small number. None. Every solid surface in the solar system records impacts, because impacts never stop. The Moon is saturated with them. Mercury is saturated. Callisto is saturated. Mimas, 400 kilometers across, carries a crater 1/3 of its own width. Cratering is the default state of a solid surface in this solar system, and the crater count is how the age of a surface is measured. Io's surface is being buried by volcanic deposits faster than craters can accumulate on it. Estimates of the resurfacing rate vary widely, from a fraction of a millimeter to several centimeters a year, and NASA's framing is that Io completely resurfaces itself roughly every million years. Which means the face Io presented to Voyager in 1979 is not the face it has now. Almost none of the terrain in those photographs still exists. The engine driving all of this is the orbit. Io is squeezed and released on every circuit around Jupiter. The solid surface rises and falls by up to 100 meters, twice per 42.5-hour orbit. That is a tide in rock, roughly 1/3 of the height of the Eiffel Tower, and the friction generated by that flexing is the heat source. This is what separates Io from Earth. Earth has a hot interior because it formed hot and has been slowly losing that heat ever since, topped up by radioactive decay. Io has a hot interior because it is being worked, continuously, from outside, by a body it cannot get away from. Picture standing on it. The ground is yellow and orange and crusted, and in places it is warm, when nothing at that distance from the sun has any business being warm. Jupiter fills 1/4 of the sky, and it does not move, because Io keeps one face toward the planet permanently, so Jupiter hangs in precisely the same position forever, banded, turning, close enough that the individual cloud belts are visible without any instrument. There is almost no atmosphere. The sky is black even in full sunlight, and the stars do not twinkle. Some distance across the plain, a plume is rising. It is not fast, and it is not violent to watch. It climbs silently, 250 kilometers, spreading into an umbrella at the top and falling back in a wide ring of sulfur dioxide snow. The whole event takes minutes, and it makes no sound at all, because there is nothing to carry sound. Under your feet, the ground rises and falls by 100 meters over the course of hours, and you would not feel it, because everything rises and falls together. And every square meter of what you are standing on is new. Younger than human civilization. It will be buried again long before anything on it has had time to be scarred. Voyager 2, arriving 4 months later in July of 1979, found that some plumes had stopped and others had started, and that the surface had visibly changed in the interval. Io has no way out of this. The resonance that drives the heating is not permanent, and on billion-year timescales, Io will drift outward, cool, and stop. But that is not relief on any timescale that means anything. For now, and for as long as anyone will be watching, it is a world being melted from the inside by a planet it circles every 42 hours. Io's mountains are worth one final note, because they are not what anyone assumes. They are not volcanoes. They are tectonic blocks, pushed up by the sheer compression of material being deposited on the surface continuously from above, and some of them exceed the height of Everest. On a world where the crust is being added to faster than anywhere else in the solar system, the crust has to go somewhere, and where it goes is up. The plumes themselves also work by a mechanism with no terrestrial equivalent. Many of them, including the class named after Prometheus, are not magma fountains at all. Flowing lava travels across the surface, encounters buried sulfur dioxide frost, and flash vaporizes it. The result is a geyser rather than an eruption, driven by frost rather than by pressure from below. Io is being cooked. The next moon along the same chain is only being warmed, and that turns out to be far more consequential. Number 8. The ice shell with an ocean underneath. Voyager 2 passed Europa on the 9th of July 1979 at a range of about 205,700 kilometers. Voyager 1 had already gone by 4 months earlier, at more than 3 times that distance, close enough to establish that Europa was smooth and bright and not much else. The July pass was close enough to resolve the surface properly for the first time. What came back was a bright white sphere covered in a global network of dark lines. The lines are called lineae. Some of them run for well over 1,000 kilometers. They cross and overlap in every direction, in every orientation, and they have almost no vertical relief at all. Standing on one, you would struggle to tell you were on it. From orbit, the pattern is unmistakable, and the description that attached itself to Europa in 1979 and has never let go is that it looks like a cracked eggshell. But the important thing about those images is not what was in them. It is what was missing. There were essentially no craters. Voyager-era analysis identified about 5 fresh large impact craters in the 10 to 30 kilometer range across the whole visible surface. To understand why that is startling, set Europa against Callisto. Callisto is another moon of Jupiter, similar in size, formed at the same time in the same system, bombarded by the same population of impactors for the same 4.5 billion years. Callisto is saturated with craters. It is the most heavily cratered object in the solar system. There is literally no room on it for another crater without erasing an existing one. 2 bodies, same age, same neighborhood, same bombardment. One keeps a complete record of it. The other keeps almost none. There is only one way to read that. Europa's surface is young, and something is erasing it. Now follow the inference, because it is a short chain and it leads somewhere significant. If a surface is being renewed, there is energy beneath it, and there is mobile material beneath it. Europa sits in the same orbital resonance chain as Io, so it is subject to the same kind of tidal flexing, weaker because it is further out, but still substantial. And Europa's surface is water ice. Tidal heating, applied to water ice, gives liquid water. The proposal that Europa has a global subsurface ocean went into print in 1979 in a paper titled "Is There Liquid Water on Europa?" written by Patrick Casson, Ray Reynolds, and Stanton Peele. Those are the same 3 names as the Io prediction, working the same physics on the next moon out. It is worth being precise about the sequence, though, because it is often told wrong. The Io paper was a genuine prediction, published before the encounter and confirmed days later. The Europa paper was contemporaneous with the flybys, not ahead of them. Io was predicted and then found. Europa was found and then explained. What later missions established turned the inference into something close to certainty. Galileo, in the 1990s, measured an induced magnetic field around Europa. As Jupiter's tilted magnetic field sweeps past the Moon, the field Europa experiences changes direction, and Europa responds by generating a field of its own. That is what a conductor does. The most plausible conductor inside an icy moon is a global layer of salty liquid water. The current picture is an ocean somewhere between 60 and 150 kilometers deep, beneath an ice shell 15 to 25 kilometers thick. That ocean holds something in the region of 2 to 3 times as much liquid water as every ocean on Earth combined. On a moon 3,122 kilometers across, which is slightly smaller than our own. There is direct visual evidence in the images as well, in the regions called chaos terrain. In those areas, the ice appears to have broken into rafts, rotated, drifted apart, and refrozen in new positions. Matching edges can be identified on blocks that are now hundreds of meters from each other and turned through significant angles, like pieces of a jigsaw scattered and reassembled carelessly. That is not a pattern that ice makes when it sits on rock. It is a pattern ice makes when it sits on liquid. Europa's surface is otherwise almost featureless in the vertical sense. The relief across the entire globe is typically under 100 to 200 meters, and the highest known feature, a dome called Cilix, is about 1.5 kilometers. It is widely described as the smoothest solid body in the solar system, and while that is a descriptive superlative rather than a formal measurement, nothing has yet displaced it. The lineae themselves are reddish-brown, and the coloring is thought to come from salts and sulfur compounds, either delivered from the ocean below or implanted from Io. And this is the reason Europa sits this high on the list, above the volcanoes and the cliffs and the storms. Every entry before this one is a strange object. This one changed the question the entire field was asking. Before Europa, the search for life beyond Earth in this solar system meant Mars, and essentially Mars alone. The reasoning was straightforward and it seemed sound. Liquid water requires warmth. Warmth requires proximity to a star. There is a band of orbital distances where a planet is neither boiled nor frozen, and outside that band, there is no point looking. Europa is 5 times farther from the Sun than Earth is. It receives about 4% of the sunlight we do. Its surface temperature is about 110 Kelvin at the equator and about 50 at the poles, cold enough that the ice behaves as a brittle solid, the same way water ice behaves like rock everywhere in the outer solar system. And it has more liquid water than we do. The habitable zone stopped being a distance from a star and became a question about tides. Every subsequent discovery in the outer solar system, at Enceladus, at Titan, at Ganymede, at Ceres, and quite possibly at Mimas, follows from the change in thinking that a spacecraft flyby forced in 1979 by returning a picture with something missing from it. The Europa Clipper mission launched in October of 2024 and is designed to make dozens of close passes. It will not land. The radiation environment near Jupiter and the unknown character of the surface make landing impractical for now, which is a familiar constraint by this point in the list. 2 more things about the ice are worth sitting with, because they change what the cracks mean. The first is that the shell is being flexed. Estimates put the tidal deformation of Europa's ice at up to 30 meters over each orbit, which is why the cracks open and close rather than simply sitting there. The lineae are not scars. They are joints, and they are working joints. Material is being drawn up into them when they open and squeezed out when they close, which is the most plausible route by which anything from the ocean reaches the surface where an instrument could sample it. The second is that we do not know how thick the shell is, and the uncertainty is not academic. 15 kilometers and 25 kilometers are very different propositions for anyone who ever wants to get through it. There are two competing pictures, one in which the shell is thin and mobile, and the ocean is close to the surface in places, and one in which it is thick and rigid, and the mobility is confined to warm ice rising within the shell rather than liquid reaching it. Both explain the surface reasonably well. Neither has won. There have also been reports, from Hubble and from other observations, of water vapor plumes venting from Europa's southern region. If they are real, they would be the single most valuable target in the outer solar system, because a spacecraft could fly through one and sample an alien ocean without ever landing on anything. The detections remain contested, and that is the honest position. Some observing runs find them and some do not. Callisto, the moon used as the comparison earlier, has one more thing to add. It is now thought to have an ocean too, buried far deeper and much colder. So does Ganymede, which is larger than Mercury. So, on the evidence from Cassini, does Enceladus, which is a fraction of the size of any of them and vents its ocean into space through fractures at its south pole. There may be more liquid water in the outer solar system in half a dozen moons of two giant planets than there is on every world inside the asteroid belt combined. All of that follows from a photograph in July of 1979 that was notable for what it did not contain. Europa is warm enough for liquid water because of tides. The next entry is the coldest surface anyone has ever measured, and it is also active. Number 7. The Geysers, on the coldest surface ever measured. On the 25th of August 1989, about 5 hours after its closest approach to Neptune, Voyager 2 passed Triton at a range of about 40,000 kilometers. It was the last solid body the mission would ever photograph closely. After Triton, there were no more targets, and there never would be again. Triton is 2,707 kilometers across, which makes it the 7th largest moon in the solar system, and it turned out to be one of the strangest objects either spacecraft encountered. Start with the temperature, because it is the record that has never been broken. Voyager measured Triton's surface at 38 Kelvin. That is minus 235 Celsius. It was, and it remains, the coldest surface temperature ever directly measured anywhere in the solar system. Pluto, which orbits considerably further out and receives less sunlight, is warmer, at around 43 Kelvin. Charon is warmer still. The reason Triton beats them is not distance. It is that Triton's surface is covered in fresh nitrogen ice, which is extraordinarily reflective, and in places approaches 99% reflectivity. It throws away almost all the sunlight that reaches it, and therefore cannot warm up. Triton is cold because it is clean. Then there is the orbit, which should not exist. Triton orbits Neptune backwards. Its orbit is inclined about 157 degrees, which means it travels around the planet in the opposite direction to the planet's own rotation. Every large moon in the solar system that formed alongside its planet, out of the same disk of material, orbits in the same direction the planet spins. That is not a rule imposed by anything. It is simply what happens when a moon condenses out of a rotating disk. Triton does the opposite, which means Triton did not form there. It has to have been captured. And capturing an object the size of Triton is genuinely difficult, because the energy has to go somewhere. An object falling toward a planet from interstellar distances arrives with too much energy to be retained. It swings past and leaves again. Something has to remove the excess. The best current explanation, published in 2006, is that Triton arrived as one half of a binary pair from the Kuiper belt. The encounter with Neptune broke the pair apart, ejected the partner at high speed, and kept Triton. The partner carried away the excess energy, which means Triton is a Kuiper belt object. It is the same class of body as Pluto, comparable in size, comparable in composition, formed in the same region of the solar system. Voyager 2 photographed one at close range in 1989, 26 years before New Horizons reached Pluto, and at the time, almost nobody framed it that way, because the Kuiper belt as a population had not yet been observationally established. Now the part nobody anticipated. The Triton images were analyzed after the encounter rather than during it, using stereo pairs and high phase angle frames, and in early October of 1989, the imaging team reported something in them. Dark columns, rising roughly 8 kilometers from the surface, and then bending sharply sideways and trailing downwind for up to 150 kilometers, settling out as dark streaks laid across the ice. At least 4 were active during the encounter. Dozens of old streaks are visible across the surface, all aligned in roughly the same direction. The analysis was led by Lawrence Soderblom of the United States Geological Survey and published the following year. It should be said that the interpretation was not unanimous. Andrew Ingersoll, an imaging team member, argued that the features were dust devils rather than geysers, and that dispute has never been fully settled. If they are geysers, the mechanism is one of the more elegant things in planetary science, and it works at a temperature at which almost nothing works. Triton's surface is nitrogen ice, and in places that ice is translucent. Sunlight passes through the upper layer. It is very weak sunlight, less than 1,000th of what reaches Earth, but it is not zero, and it is absorbed by darker material a meter or two underneath. That warms the buried layer by a few Kelvin. At 38 Kelvin, a few Kelvin is an enormous relative change. Nitrogen sublimates. Pressure builds beneath a sealed lid of ice. Eventually, the lid ruptures, and the gas vents, carrying dark material with it, 8 kilometers up. It is a greenhouse effect operating at -235 Celsius, driven by a sun that from Triton's distance is not a disk at all. It is a point of light, 900 times fainter than from Earth, bright enough to cast a sharp shadow, and nothing more. Triton has an atmosphere as well, which almost nothing that small does. It is nitrogen-dominated, at a surface pressure commonly quoted as 14 microbars, with the Voyager radio occultation retrieval closer to 16. That is about 1/70,000th of Earth's atmospheric pressure. It is thin enough to be effectively vacuum for any practical purpose, and thick enough to raise thin clouds and haze layers on the horizon, and thick enough to produce a wind, which is what bends the plumes sideways and lays them down in parallel streaks. Large areas of the surface are covered in a terrain of dimples and ridges 30 to 40 kilometers across, which was named cantaloupe terrain for its resemblance to melon rind. It has no counterpart anywhere else in the solar system. The leading idea is that it formed by denser material sinking and lighter material rising through a soft icy crust, but nobody has reproduced it convincingly. There are also very few impact craters on Triton, which by now is a familiar signal. The surface is young. Something has been resurfacing it at 38 Kelvin within the recent geological past. Picture standing there. Nitrogen frost underfoot, pink and white, catching what little light there is. The sun is a point, and the shadows it casts are sharp and almost black, because there is essentially no atmosphere to scatter light into them. Neptune hangs overhead, deep blue, taking up a substantial piece of the sky. And it moves across that sky in the wrong direction, because this moon travels backwards around it. Somewhere out on the plain, a column of dark gas is rising 8 kilometers, silently, in slow motion, and then flattening at the top and running downwind for 150 kilometers, laying a dark stripe across the ice that will still be there in a century. There is an ending to this, and it is not a gentle one. Triton's retrograde orbit is decaying. Tidal interaction with Neptune is drawing it steadily inward, and in something on the order of 3.5 billion years, it will pass inside the Roche limit and be pulled apart. Neptune will acquire a ring system considerably brighter than Saturn's, made from the Moon. Only about 40% of Triton was imaged at useful resolution. The rest was either in darkness or presented at an angle from which nothing could be resolved. That is the same constraint that applied at Miranda, for the same reason, and it applies to almost every moon either spacecraft encountered. A flyby is a single pass at a single geometry, and the hemisphere that happens to be facing the wrong way stays unphotographed indefinitely. Triton has also been changing since Voyager left. Ground-based observations through the 1990s and 2000s, watching Triton pass in front of stars, suggested that its atmosphere had thickened measurably since 1989. That is consistent with a seasonal cycle, and Triton's seasons are unusually complicated. Its rotation axis, its orbit around Neptune, and Neptune's orbit around the Sun all precess against one another, so the pattern of which region gets sunlight repeats on a cycle of several centuries rather than annually. There is one more measurement that matters. Triton's density is about 2.06 grams per cubic centimeter, which is high for an icy body. That makes it roughly 2/3 rock by mass, and rock means radioactive decay, and radioactive decay means internal heat. Combined with tidal heating from its still settling orbit, that is very likely enough to maintain a subsurface ocean underneath the nitrogen and water ice, which would mean the coldest surface ever measured has liquid water under it. Cold, on the evidence of the outer solar system, has almost nothing to do with whether a world is dead. Triton was 5 hours after the closest approach of the entire mission, and the planet it orbits had already produced the fastest winds anyone has ever measured. Number 6. The fastest winds ever measured, on the faintest planet. Voyager 2 reached Neptune on the 25th of August 1989 at 3:56 in the morning, Universal Time, passing roughly 4,950 kilometers above the North Polar cloud tops. About 3,000 miles. That was the closest approach the mission ever made to any planet, and it was flown deliberately close in order to bend the trajectory down toward Triton afterward. It came 12 years and 4 days after launch. It remains the only visit anyone has ever made to Neptune, and there is no approved mission to return. Consider what was reasonable to expect. Neptune is 30 times further from the Sun than Earth. It receives about 1,000th of the sunlight. 3 years earlier, Uranus, which is closer in, had turned out to be a blank blue-green disk with essentially no visible weather. The reasonable prediction for Neptune was a darker, colder, quieter version of the same thing. What arrived instead was a deep blue planet with visible, structured, violent weather. There were high white cirrus clouds of methane ice, and Voyager photographed them casting shadows onto a cloud deck 50 kilometers below. Neptune is the only planet in the outer solar system where cloud shadows have ever been imaged, and those frames gave a direct measurement of the vertical separation between cloud layers rather than an inferred one. There were bright bands. And in the southern hemisphere there was an enormous dark oval, roughly 13,000 by 6,600 kilometers, large enough to contain the entire Earth. It was named the Great Dark Spot. It is not a storm in quite the way the Great Red Spot is. The current understanding is that it is a hole in the methane cloud deck, a gap through which the darker atmosphere at greater depth shows through. What holds the hole open is an anticyclonic circulation, and the whole feature drifted westward at about 30 meters per second relative to the surrounding air, without staying locked in latitude the way Jupiter's spot does. Then the imaging team tracked the clouds and measured the wind speeds, and the numbers did not make sense. NASA's current planetary facts give Neptune winds above 2,000 kilometers per hour. The figure most often quoted for the winds at the edge of the Great Dark Spot is 2,100 kilometers per hour, about 1,300 miles per hour. Those are the fastest winds ever measured on any planet in the solar system. They are supersonic with respect to Neptune's own atmosphere, and they are blowing on the planet that receives less sunlight than any other planet there is. That is a genuine problem in physics, and it is not solved. Weather is normally driven by a star. Sunlight heats one region more than another. Air moves from the warm region to the cold one, and the planet's rotation organizes the flow into cells and jets. On Neptune, the sun contributes almost nothing. 1,000th of Earth's illumination cannot possibly drive winds 4 times faster than anything in Earth's atmosphere. So the energy is coming from inside. Neptune radiates about 2.6 times as much energy as it receives from the sun. Something in its interior is still hot and still releasing heat, and that heat is stirring the atmosphere from below. Where it comes from is not settled. Neptune should have finished cooling by now. And the comparison that makes it worse is sitting one orbit inward. Uranus, nearly identical in size, nearly identical in composition, radiates almost no excess heat at all, which is exactly why its atmosphere is bland and blank. 2 planets of the same class, formed in the same region, in the same era, out of the same material. One is dead, and the other is storming, and there is no accepted explanation for the difference. Voyager tracked one more feature worth naming. Between the dark spots there was a bright chevron-shaped cloud, moving fast enough to complete a circuit of the planet in about 16 hours, and the imaging team nicknamed it the Scooter. Its nature was never determined. It has not been seen since. Then there is what happened next, which is the part of this entry that gives it its place on the list. In 1994, 5 years after the encounter, the Hubble Space Telescope looked at Neptune. The Great Dark Spot was gone. So was a second feature, Dark Spot 2. Not moved. Not faded. Absent. New dark spots have appeared since, at other latitudes, and have vanished in their turn. But the feature Voyager photographed, the one in every textbook, the one that appears whenever anyone illustrates Neptune, no longer exists. And there is no photograph of it from any other spacecraft, because no other spacecraft has ever been there. Those images are the only record of a structure the size of the Earth, and the structure is gone. The rings were a genuine puzzle resolved. Occultation observations from Earth, starting in 1984, had detected material around Neptune, but only on one side of the planet. That implies incomplete rings, arcs rather than circles, and arcs are dynamically difficult because orbital shear should spread them into a full ring within a fairly short time. Voyager 2 confirmed it. The outermost ring, Adams, at about 62,900 kilometers, carries distinct clumps of material. The French team who had made the occultation detections named them Liberté, Égalité, Fraternité, and Courage. They are held in place by a small moon called Galatea, and some of them have visibly faded in the decades since, with at least one appearing to be decaying. And Voyager discovered 6 new moons in that single pass: Proteus, Larissa, Despina, Galatea, Thalassa, and Naiad. Proteus, at about 420 kilometers across, is larger than Nereid, which had been known since 1949 and had been assumed to be Neptune's second largest moon for 40 years. Proteus is right at the size boundary where a body's own gravity should pull it into a sphere, and it is irregular, which suggests it froze into shape before it had the chance to relax. Neptune's own rotation period is about 16 hours and 6 minutes, and its magnetic field, like Uranus's, is badly misaligned, tilted about 47 degrees and offset from the planet's center. Two ice giants, two broken magnets. Whatever process generates those fields, it is not the process that generates Earth's, and Voyager 2 is the only spacecraft that has ever measured either of them. A word about the color, since it is the first thing anyone notices. Neptune is blue because methane in its atmosphere absorbs red light and lets blue through. So is Uranus, for the same reason and with roughly the same amount of methane. But Neptune is a deep, saturated, almost artificial blue, and Uranus is a pale, washed-out green. Composition alone does not account for the difference. The current thinking involves a haze layer that is thicker at Uranus and thinner at Neptune, but the explanation is recent and not fully settled, and it is a slightly uncomfortable thing to admit about 2 of the 8 planets. There is also the matter of the year. Neptune takes 165 Earth years to go around the Sun. It was discovered in 1846, which means it completed its first full orbit since anyone knew it existed in 2011. 1 Neptunian year has elapsed in the entire history of the planet being known. And within that single year, the only spacecraft visit lasted a few hours. Which brings the 2 ice giants together in a way worth stating plainly. Uranus and Neptune are the 2 largest unexplored objects in the solar system. Between them, they hold most of the mass of the outer planets that is not Jupiter or Saturn. Every close-range measurement of either of them was collected by 1 spacecraft in 2 encounters 3.5 years apart in the 1980s, using instruments designed in the 60s and built in the 70s. These are the only photographs that exist. At Uranus, that meant the data is thin. Here it means something sharper, because the largest feature in those photographs has since ceased to be there. That was the last planet. 9 years earlier, the other spacecraft had already given up its last planet on purpose. Number 5. The moon we flew to and still could not see. On the 12th of November 1980, at 41 minutes past 5 in the morning, Universal Time, about 18 hours before its closest approach to Saturn, Voyager 1 passed Triton at 6,490 kilometers from the Moon's center. That is an altitude of roughly 3,900 kilometers above the surface. It was the single most carefully protected observation of the entire mission. The trajectory had been designed around it years before launch. Everything else at Saturn was arranged to accommodate it, and the cameras returned an orange ball with nothing on it. The choice that made that encounter possible is routinely told wrong, so it is worth stating precisely. Voyager 1's Titan flyby required a trajectory that threw the spacecraft up and out of the plane of the solar system afterward. There was no way to do it and remain in the plane. Had Titan been skipped, Voyager 1 could have continued on from Saturn to Pluto, arriving in roughly the spring of 1986. That was a real option. It was in the planning documents. It was discussed. Titan 1. What Voyager 1 did not trade was Uranus and Neptune. That is the common version, and it is wrong. Voyager 2 carried the Uranus and Neptune option, and it also carried a backup Titan flyby, which, if it had been needed, would have destroyed the outer legs entirely. So the accurate accounting is this. Voyager 1 gave up Pluto to look at Titan. And because it succeeded at Titan, Voyager 2 was released from the backup obligation and allowed to go on to Uranus and Neptune. One spacecraft's decision bought the other spacecraft 2 planets and cost the mission a third. The people making that call were the Voyager science team, working from an architecture laid down before launch and reaffirmed after Pioneer 11 passed Saturn in September of 1979, with Ed Stone as project scientist. And here is the part that gives the decision its weight. Pioneer 11 had already returned a low-resolution image of Titan, and it already showed a featureless disk. The warning was on the record. They knew, before they committed, that the haze was probably thick enough that the cameras would see nothing. They flew the trajectory anyway. It was a considered irreversible choice, made with incomplete information, accepting that the most protected observation in the mission might return an orange circle. It was the right call, and it can be defended on the evidence. But Pluto then waited another 29 years for a spacecraft, and most of the people who made that decision did not live to see the photographs New Horizons sent back. What the cameras actually saw was nothing at all. A featureless orange sphere with a slightly darker northern hemisphere and a thin, detached layer of haze visible above the limb. Voyager's cameras were Vidicon tubes, sensitive in visible light. Titan's atmosphere is filled with a photochemical aerosol haze that is optically thick right across the visible spectrum, and it is globally uniform. There were no gaps in it. There was no weather to see through, no break, no thinner region. The surface of Titan stayed invisible for another 2 decades, until Cassini and the Huygens probe got beneath it using infrared windows and radar. But the imaging failing is only half the encounter, and the other half succeeded completely. As Voyager passed behind Titan as seen from Earth, its radio signal cut through the atmosphere on the way in and again on the way out. The way that signal bent, weakened, and shifted in frequency gave a complete profile of the atmosphere it was passing through. Radio occultation does not care about haze at all. The numbers that came back were remarkable. Surface pressure, 1,496 millibars, plus or minus 20. That is 1.5 times Earth's atmospheric pressure at sea level, on a moon with about 2% of Earth's gravity. Surface temperature, 94.0 Kelvin, plus or minus 0.7. Minus 179 Celsius. Radius of the solid body, 2,575 kilometers. Combining the occultation with ultraviolet and infrared spectrometry gave the composition, and it settled a long-running argument. Titan's atmosphere is nitrogen-dominated, at least 82% and probably above 90%, with a few percent methane. That vindicated a minority position, argued for years by Donald Hunton, against a widely held assumption that the atmosphere was mostly methane. Titan and Earth are the only 2 bodies in the solar system with thick nitrogen atmospheres. That is the sentence that made Titan a permanent priority. The orange color comes from organic chemistry running continuously. Ultraviolet light and charged particles break apart nitrogen and methane in the upper atmosphere, and the fragments recombine into progressively larger and more complex molecules, which eventually rain out as aerosol. Carl Sagan and Bishun Khare coined the word tholin for those substances in a paper published in 1979, roughly 20 months before the flyby. So Voyager did not discover tholins either. What it found was the optically thick organic smog that laboratory work had already predicted, and it confirmed that a moon in the outer solar system is manufacturing complex organic chemistry out of sunlight and air, continuously, and has been for a very long time. There was one more result, and it was a demotion. Before Voyager, Titan was believed to be the largest moon in the solar system. A lunar occultation measurement in 1974 had given a diameter of about 5,800 kilometers, comfortably larger than Ganymede. Every pre-Voyager measurement had in fact been measuring the top of the haze, rather than the ground. Voyager's occultation gave the solid body as 5,152 kilometers across. Ganymede is 5,268. Titan lost the record on the day it was first properly visited. So the ledger on this encounter reads as follows. Voyager 1 gave up the only realistic chance at Pluto for 35 years. It flew closer to Titan than to any other body it ever encountered. Its cameras returned a blank. Its target lost the record it was famous for. And the radio science established that there is a world out there with a thicker atmosphere than Earth's, made mostly of nitrogen, with a surface at -179 Celsius, where methane can exist as a liquid. Cassini and Huygens later found what was under the haze. Lakes and seas of liquid methane and ethane near the North Pole. River channels. Dunes made of organic sand. A probable subsurface water ocean. A surface pressure at which a human being would need warmth and oxygen but no pressure suit, and gravity low enough and air thick enough that a person with wings strapped to their arms could fly. The trade was Pluto for an orange circle. It was worth it. It is worth staying inside that encounter for a moment, because the experience of it was strange for the people running it in a way that the summary does not convey. The spacecraft was closing on Titan at tens of thousands of kilometers per hour, and the mission had been aimed at this moment for 3 years. The cameras ran their sequence automatically, on a timeline written months earlier. Then the frames came down over the following hours, one at a time, across 1.5 billion kilometers, with light itself taking 1 hour and a quarter each way. In the imaging room, the pictures assembled line by line on the screens, the way all Voyager images did, building down from the top. Orange. Uniform orange. A slightly darker band in the north. The limb and a thin separate line of haze standing above it. Nothing else. No coastline. No crater. No cloud. No shadow. Something was down there, and everyone in the room knew it, because within hours the radio data would say the surface pressure was half again Earth's. But whatever it was would not be seen by anyone in that room, and most of them understood immediately that it would not be seen in their working lifetimes either. And all the while, invisibly and without any camera involved, the radio signal was slicing through the atmosphere on its way past and returning everything the cameras could not. There are a few more figures that fill Titan in. The atmosphere extends nearly 10 times higher than Earth's before it thins out, because the gravity is so weak that it cannot pull the air down. The detached haze layer Voyager photographed at the limb sits several hundred kilometers above the surface, and it was itself an unexpected structure that took decades to model properly. Titan is the only moon in the solar system with a substantial atmosphere. The next thickest belongs to Triton, and Triton's is roughly 70,000 times thinner. And there is an open problem in the chemistry that has never been closed. Methane in Titan's atmosphere is destroyed by sunlight on a timescale of tens of millions of years. It converts to heavier hydrocarbons, rains out, and does not come back on its own. Titan is 4.5 billion years old. So something is resupplying the methane, continuously, and nobody knows what. The candidates involve outgassing from the interior, or cryovolcanism, or release from a subsurface reservoir, and none of them has been demonstrated. Which means the atmosphere Voyager measured, the 1.5 bars of nitrogen that made Titan permanently interesting, is being maintained by a process nobody has identified. The Dragonfly mission, a nuclear-powered rotorcraft designed to fly between sites on Titan's surface and land at each one, is scheduled to launch later this decade. It exists because of a radio occultation performed in 1980 by a spacecraft whose cameras had just failed to see anything at all. After Titan, Voyager 1 had nothing left in front of it but the edge of the Sun's territory. It took another 32 years to get there. Number 4. The edge of the Sun's territory. The Sun does not simply light the solar system. It inflates it. The solar wind is a continuous outflow of charged particles, leaving the Sun at several hundred kilometers per second in every direction, and it blows a bubble in the interstellar material the Sun is moving through. That bubble is called the heliosphere, and everything anyone has ever touched, launched or lived on sits inside it. A bubble has a boundary. Nobody knew where that boundary was, or what it was like, or even whether it was a sharp thing or a gradual one, until 2 spacecraft crossed it and reported back. There are 2 boundaries, in fact, and they are different in kind. The first is the termination shock. This is where the solar wind, which has been traveling supersonically since it left the Sun, runs into the interstellar material ahead of it and abruptly slows down, compresses, and heats up. It is the same phenomenon as the standing ring you can see in a kitchen sink when the tap runs onto a flat surface, scaled up by a factor of roughly 100 billion. Voyager 1 crossed the termination shock on the 16th of December, 2004, at 94 astronomical units. An astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers, so 94 of them is around 14 billion kilometers. Voyager 2 crossed on the 30th of August, 2007, at 83.7 astronomical units, roughly 10 astronomical units closer in. That difference is a result in its own right, and it is a good example of why 2 spacecraft are worth more than twice one. The 2 probes were traveling in substantially different directions. They found the same boundary at significantly different distances, which means the heliosphere is not a sphere. It is asymmetric, pushed in on one side and drawn out on the other, shaped by the Sun's motion through the galaxy and by the interstellar magnetic field pressing on it. Voyager 2 also crossed the termination shock at least 5 separate times within a few days, because the boundary itself was moving in and out across the spacecraft as solar activity varied. The edge of the solar system breathes, on a timescale of days and also on the 11-year cycle of the Sun, moving by several astronomical units. And because Voyager 2's plasma instrument was still working, that crossing produced the only direct in situ measurement of the plasma at a stellar termination shock that has ever been made or is likely to be made in the foreseeable future. Voyager 1 could not do that because its plasma instrument had failed in 1980, 24 years before it needed it. The second boundary is the heliopause. This is the outer wall, the place where the solar wind finally stops pushing and interstellar plasma takes over. Voyager 1 crossed it on the 25th of August, 2012, at about 121.6 astronomical units. Voyager 2 crossed on the 5th of November, 2018, at 119, and its transition took under a day. How Voyager 1's crossing was proved with a plasma instrument that had been dead for 32 years is the finest piece of improvisation in the mission's history, and it deserves to be told properly. Density of charged particles is what distinguishes the inside of the heliosphere from the outside, and Voyager 1 had no way to measure it. But it had a plasma wave instrument built at the University of Iowa, designed to listen to electric field oscillations. Here is the trick. When a shock wave from a solar eruption sweeps past the spacecraft, it disturbs the plasma around it, and the plasma rings. It oscillates at a natural frequency, the way a wine glass rings at a frequency set by its shape. And the natural frequency of a plasma depends on one thing only: the density of electrons in it. So if you can hear the ring, you can calculate the density. You do not need to touch the plasma at all. You need a wave detector, patience, and a solar eruption to arrive at the right moment. 2 such events were used. The first ran from the 23rd of October to the 27th of November, 2012, and was only found retrospectively in data that had already been on the ground for months. It gave about 0.06 electrons per cubic centimeter. The second ran from the 9th of April into May of 2013 at about 2.6 kilohertz and gave about 0.08. Out in the heliosphere, The density had been running around 0.002. The jump was roughly 40-fold, and that is the signature of interstellar space. Donald Gurnett of the University of Iowa, who had led the Jupiter lightning analysis 34 years earlier, led this one too. The announcement came on the 12th of September 2013, a full year after the crossing itself had happened. One correction that circulates widely and should be fixed. The shock that triggered the April 2013 oscillations left the Sun in March of 2011. It took roughly 13 months to get there. It is not an April 2013 solar event, and the delay is itself a measure of how far away the spacecraft was. Then there is the result nobody expected, which has still not been properly explained. Everyone assumed that when a spacecraft crossed into interstellar space, the magnetic field direction would change. The Sun's field and the galaxy's field point in different directions. That was the obvious signature to look for, and it was in every model. The field strength did jump, roughly doubling, from about 0.2 to 0.4 nanotesla. The direction barely changed at all. That is why the crossing was initially argued to be something else, a transitional region that was named the magnetic highway, rather than a true boundary. It took the plasma density measurement to settle the argument. And when Voyager 2 crossed 6 years later with a working plasma instrument, it saw exactly the same thing. The field turns almost not at all. Nobody has a good account of why the interstellar magnetic field near the Heliopause should be so nearly aligned with the Sun's. Crossing the boundary also flipped the particle environment completely. Low-energy particles coming from the Sun fell away. Galactic cosmic rays, the high-energy nuclei that come from the rest of the galaxy, from supernovae and from processes far outside this solar system, rose over about 2 to 3 days and roughly doubled. That is a direct measurement of how much shielding the heliosphere provides. The Sun's magnetic bubble deflects roughly half of the galactic cosmic ray flux before it reaches the inner solar system, and the only way anyone knows that number is that 2 machines stepped outside and counted. 2 more items attached to this boundary need handling honestly because both have been badly reported. The first is the wall of fire. Voyager 2's working plasma instrument measured the local interstellar plasma at somewhere between 30,000 and 50,000 Kelvin, hotter than the 15 to 30,000 that had been expected. That number was reported very widely as a wall of fire at the edge of the solar system, sometimes rendered in Fahrenheit to make it larger. The temperature is real. The framing is not, and the phrase is a media coinage rather than anything the Voyager team ever said. Temperature measures how fast individual particles are moving. Heat measures temperature multiplied by how many particles there are. At roughly 1/10 of a particle per cubic centimeter, there is essentially nothing there to transfer heat with. Neither spacecraft warmed by any measurable amount going through it. It is the same distinction that came up earlier with the Io torus, where the ions sit at 1,000,000 Kelvin, and the environment is nevertheless not hot in any sense that would matter to anything. The second is the hydrogen wall. Both Voyager's ultraviolet spectrometers recorded an excess of ultraviolet emission from hydrogen in the outer heliosphere, which is consistent with a pileup of neutral hydrogen slowing against the heliopause. In August of 2018, the New Horizons spacecraft found a comparable constant background brightness after a calibration correction was applied. The correct phrase is consistent with. The New Horizons team explicitly allowed that a distant background source could produce the same signal. This is a strong hypothesis, not a confirmed structure, and it should be presented as one. Now consider what the crossing was actually like. There is nothing to see. That is the whole character of it. The spacecraft is 18 billion kilometers from home. The Sun is a point of light, still by far the brightest thing in the sky, but a point with no disk at all. Over a period of days, the character of the space around the machine changes completely. The thin wind that has been blowing outward from that point of light for the entire existence of the solar system stops. The particles pressing in from outside, from the galaxy, from stars that died before the sun existed, become the local environment. The magnetic field strength doubles, and its direction, unaccountably, holds. No instrument sees anything. There is no camera running. The cameras have been off for 22 years. There is no line, no wall, no flash, nothing that would register on any human sense. There is only a slow change in the numbers being written by a set of instruments built in the early 1970s, arriving on Earth 17 hours later at the speed of light and taking another year to be understood. Outside the boundary, everything went quiet. And then, in 2017, the quiet turned out not to be quiet. Number 3. The sound of interstellar space. Everything Voyager 1 had detected in interstellar space up to that point was an event. A shock wave arrives from the sun. The plasma rings. The density can be calculated from the ringing. Then the ringing stops, and it goes quiet again, sometimes for years, until the next eruption happens to arrive. 2 usable events in the first several years past the boundary. Between them, nothing. In May of 2021, a paper reported that this was not the whole picture. The work was led by Stella Koch-Ocker, then a doctoral student at Cornell University, and what she found in the plasma wave data was a faint, persistent, extremely narrow signal at about 3 kilohertz. Not an event. A constant, present continuously since 2017. Its bandwidth is around 40 hertz. To put that in some perspective, 40 hertz is roughly the width of a single low note on a piano. The signal is not a rumble or a rush. It is one very quiet, very steady tone, occupying almost no range of frequency at all, and it never stops. And it encodes the density. That is what turned this from a curiosity into a genuinely important measurement. The discrete events gave snapshots, separated by years, of how dense the interstellar medium was at particular points along the trajectory. The continuous signal gives a reading roughly every 3 days, across about 10 astronomical units of travel. A series of snapshots became a continuous record. The value that comes out is about 0.11 electrons per cubic centimeter. But the value is not the point. The variation is, because the measurement is continuous, it shows structure, and the structure is the result. The interstellar medium is not smooth. It is turbulent on scales of an astronomical unit, with the density rising and falling from place to place in ways that no series of discrete measurements could ever have revealed. The space between the stars has weather, or something enough like weather that the distinction stops being useful. It should be said plainly what this is not. It is not sound. There is no air, and there is nothing for a sound wave to travel through. These are oscillations in an electric field picked up by an antenna and converted into audio only so that a human being can perceive the pattern in them. Calling it a hum is a metaphor. It is also a good metaphor, and the person who found it used it herself, describing the signal as faint and monotone because it occupies such a narrow band of frequency. What produces it is not settled. Thermally excited plasma oscillations and quasi-thermal noise are both on the table. Nobody should assert a mechanism, and this script will not. But the larger frame is worth stating. This is the sound of the room the solar system has been sitting inside for 4.5 billion years, and until 2017, nothing had ever been in a position to listen to it. Every measurement made before 2012 was made inside the sun's own bubble, where the solar wind drowns everything else out. It is the reason nobody could measure it from here. It is not a question of instrument sensitivity or of building a better detector. It is that the sun is too loud, and the only way to hear anything is to leave. The measurement exists because one spacecraft got far enough from the sun to be quiet, and because one instrument that was never designed to do this survived long enough to do it. That instrument is now one of only two still operating on Voyager 1. The inventory is worth reading in full because it is a list of what has been switched off. The plasma instrument failed in 1980. The cameras were switched off in 1990. The cosmic rays subsystem was switched off in February of 2025. The low-energy charged particle instrument was switched off in April of 2026. What remains on Voyager 1 is the magnetometer and the plasma wave instrument. Two senses. Voyager 2, which lost its plasma instrument in September of 2024, and its low-energy charged particle instrument in March of 2025, still has three. The shutdowns are not failures. They are decisions, and the arithmetic behind them is simple and unforgiving. Both spacecraft are powered by radioisotope thermoelectric generators running on plutonium-238, which has a half-life of 87.7 years. They lose about 4 watts of available power every year. They are now down to roughly 2/3 of their original output, and the decline is not only from radioactive decay. The thermocouples that convert the heat into electricity are degrading as well, so the loss runs slightly ahead of the physics. Every instrument switched off buys a few watts, and a few watts buys a few more months for the ones that are left. Current projections have at least one instrument operating into the 2030s. After that, the spacecraft continue on their trajectories in silence. Some numbers to hold on to while that is still true. Voyager 1 is currently around 172 to 173 astronomical units from the Sun. That is about 15.9 billion miles. Voyager 2 is around 143 to 145. On the 18th of November 2026, at 16 minutes past 2 in the morning Pacific time, Voyager 1 will reach a distance of exactly one light day. 16,094,799,096 miles. It will be the first object built by human hands to be a full day of light travel away from the planet it was built on. Signals from it already take a little under a day each way. A command sent now is executed almost a full day later and acknowledged a full day after that. There is no conversation possible with either spacecraft. There is only sending, waiting, and receiving. The signal arriving at Earth from Voyager 1 is on the order of a tenth of a billionth of a billionth of a watt. It is detected by the Deep Space Network, and in Voyager 2's case by exactly one antenna in the world, DSS-43 in Canberra, which is the only dish capable of transmitting to it because of the southerly trajectory it took after Neptune. When that antenna was taken offline for upgrades in 2020, Voyager 2 could be listened to, but not spoken to for 11 months. And the machine producing that signal has 69.5 kilobytes of memory across 3 double redundant systems, which is 6 computers in total. That is the figure from the opening of this list. It is worth returning to it here because this is what it did. That memory, that hardware, and a plasma wave antenna designed in the 1960s are what produced the first continuous measurement of the density of the space between the stars. There is something worth noticing about how this result came about, because it is the third time on this list that the same pattern has appeared. The plasma wave instrument was built at the University of Iowa in the 1970s to study waves in the magnetospheres of Jupiter and Saturn. That was its job. That was the entire justification for its mass and its power budget and its place on the spacecraft. It did that job, and it did it well, and it found the whistlers from Jovian lightning in 1979. Nobody designing it in 1972 was thinking about interstellar plasma turbulence, because nobody knew there would be a spacecraft in interstellar plasma to measure it with. The mission was 4 years long. Then it detected the density jump that proved the Heliopause crossing, using a technique nobody had planned for, because a different instrument had failed. And then it detected a continuous signal from the local interstellar medium, 44 years after launch, in a place the spacecraft was not designed to reach, at an age no one had planned for it to attain. An instrument built for one purpose, used for a second purpose because of a failure, producing a third result nobody had conceived of, half a century later, from outside the solar system. That is not luck, exactly. It is what happens when durable general-purpose instruments are sent somewhere and then kept alive by people who keep finding reasons to. Which leaves one more thing on board. And unlike everything else on this list, it was not built to measure anything at all. Number 2, the message that will outlive everything that made it. Bolted to the side of each Voyager is a 12-inch gold-plated copper phonograph record in an aluminium cover with a cartridge and a stylus, intended to be played at 16 2/3 revolutions per minute. It is worth saying that plainly and letting it sit, because the object is genuinely peculiar. The most advanced machines of their generation, carrying instruments that would go on to measure the boundary of the sun's influence, each have a record player attached to the outside. On the record, there are 115 images encoded as audio. 116 if you count the calibration frame that shows a finder what a correctly decoded picture should look like. There are greetings in 55 languages, including 5 that nobody has spoken for thousands of years. There is about 90 minutes of music. There is a 12-minute montage of about 35 sounds of Earth. There is a written statement from President Jimmy Carter and a spoken greeting from the United Nations Secretary-General, Kurt Waldheim. The music is a genuine attempt at a global selection rather than a Western one. Bach, Beethoven, Mozart, and Stravinsky are on it. So are Javanese gamelan, a Navajo night chant, Solomon Islands panpipes, a Peruvian wedding song, and Blind Willie Johnson's Dark Was the Night, Cold Was the Ground, which is a piece of music with no words in it at all, only a man humming and playing slide guitar. And Chuck Berry's Johnny B. Good. The images include human anatomy, a fertilized egg, a supermarket, a highway, a page of Newton's writing, and photographs of the Earth and its neighboring planets as they were understood in 1977. The whole thing was assembled in about 6 weeks under severe time pressure. Carl Sagan chaired the committee. Timothy Ferris produced it. The 55 greetings were recorded at Cornell after arrangements to use United Nations delegates fell through. There is one recording on it that most summaries leave out, and it is the strangest thing either spacecraft carries. Anne Druyan was the record's creative director. In early June of 1977, at Bellevue Hospital in New York, she had about an hour of her own brain activity and heartbeat recorded, with electrodes, and that recording was compressed into roughly a minute of data and put on the record. 2 days before, she and Carl Sagan had agreed to marry. During the hour she was hooked up to the instruments, she thought, in sequence, about the history of the Earth, about the development of civilization, and about what it is like to fall in love. That is on both records. It is in interstellar space right now. It has been for over 48 years. The cover is the instruction manual, and it is one of the most carefully thought-out objects ever manufactured because it has to be legible to a reader with no shared language, no shared units, no shared history, and no shared biology. It shows how to play the record and at what speed. It shows how to decode the images into a picture. It carries a map, the sun's position given relative to 14 pulsars, each identified by its rotation period, written in binary. Pulsars slow down at known rates, so that MAP does not just locate the origin in space. It locates it in time. A finder can work out where the record came from and roughly when it left. The unit used throughout is the hyperfine transition of hydrogen. That is the flip of an electron's spin in the most common atom in the universe, and it gives a frequency and therefore a time and a length that any physicist anywhere would recognize without being told. The cover measures itself in terms of the universe rather than in terms of Earth. And electroplated onto the aluminium is a patch of ultra-pure uranium-238 with a half-life of 4.468 billion years. A finder who measures how much of it has decayed can read off directly how long the record has been traveling. It is a clock that requires no maintenance, no power, and no explanation. The survival estimate attached to the record is about 1 billion years. That figure traces back to the mission's own framing rather than to a modern engineering assessment. In interstellar space, there is essentially no erosion, no atmosphere, no chemistry, and only the occasional dust grain arriving at high speed. Nobody has a strong basis to improve on the estimate, and nobody has a strong basis to dispute it either. Now the trajectories, which are the part that puts this entry at number 2. Neither spacecraft is aimed at anything. There were no targets because there was no propulsion budget to choose one. Where they are going is simply where the last gravity assist left them pointing. In roughly 40,000 years, Voyager 1 will pass within about 1.6 light-years of a small star in the constellation Camelopardalis, catalogued as AC plus 79 3888, and also known as Gliese 445. Around the same time, Voyager 2 will pass within about 1.7 light-years of Ross 248 in Andromeda. Those are close passes only in the sense that 1.5 light-years is close. It is about 9 trillion miles of missed distance. Neither is an encounter. Neither star has any known planets. Nothing will happen. And the probability of either record ever being found is, for all practical purposes, 0. A spacecraft the size of a small car, moving through a galaxy that is almost entirely empty, with no beacon, no power, and no way to be detected, is not going to be intercepted. That was understood at the time. Everyone involved understood it. The record was made anyway, which is why it belongs here, one place from the end of this list. It is the only object human beings have ever built whose intended audience does not exist, and whose expected lifespan exceeds the expected lifespan of the things that made it. It will outlast the languages recorded on it. It will outlast the countries that submitted them. On the timescale of its own survival estimate, it will outlast the species, and it will outlast the surface features of the planet. Roughly 1 billion years from now, the sun will be bright enough that the Earth's oceans will have gone. The continents will have rearranged themselves several times over. Nothing recognizable from 1977 will remain anywhere on the planet. The record will still be intact, still traveling, still carrying an hour of one woman's brain activity from a day in June of 1977, still playable at 16 2/3 revolutions per minute, with the instructions on the cover, and a patch of uranium quietly counting off how long it has been since anyone made anything. A few clarifications, since a good deal of folklore has accumulated around the record. The story that a record label blocked the use of a Beatles song is disputed by the record's own producer, who has said the track was never seriously in play. It circulates constantly, and it should not be stated as fact. The pulsar map on the cover is not original to Voyager. It is a refined version of the design used a few years earlier on the plaques carried by the 2 Pioneer spacecraft, which are also on their way out of the solar system and which are also never going to be found. And the languages on the record run from Akkadian and Hittite, which have been dead for millennia, to Mandarin and Wu, which are spoken by more people than any other languages on Earth. A finder decoding them would have no way to tell which was which, or that the gap between the oldest and the newest is about 4,000 years, which is a rounding error against the object's own expected lifetime. There is one more comparison worth making before this list reaches its last entry. Both spacecraft have now been traveling for over 48 years, and between them they have covered more distance than any other object human beings have made. Both passed the orbit of Pluto decades ago. Neither will come within many light years of any star for tens of thousands of years, and neither has any means of stopping, changing course meaningfully, slowing down, or being retrieved. They are not exploring anymore, in the sense of going somewhere. They are simply going. The trajectory was set by the last planet each one passed, and it will not change again for as long as either object exists. Which means the record is not being delivered anywhere. It is being carried, indefinitely, by a vehicle that has stopped having a destination, and the carrying is the entire point. The record was meant to be found. The last thing either spacecraft ever did with a camera was aimed in the opposite direction. Number 1. The photograph taken looking back. On the 14th of February 1990, Voyager 1 turned its cameras around for the last time. At 48 minutes past 4 in the morning, Greenwich time, it photographed the Earth. At 22 minutes past 5, 34 minutes later, the imaging system was commanded off permanently. The distance was 3.7 billion miles. 6 billion kilometers. About 40 times the distance from the Earth to the Sun. In the frame, the Earth occupies about 12/100ths of 1 pixel. That is the entry at the top of this list, and it is worth going through slowly, because almost everything about how it came to exist is stranger than the image itself. Start with the sequence it belonged to. The Earth frame was one of 60 images, taken in a single operation, covering the whole solar system from outside it. It has been called the family portrait ever since. The assembled public version uses about 38 wide-angle frames, plus 6 enlarged close-ups of individual planets, and the version JPL built on a wall ran over 20 feet long. It contains the Sun, Venus, Earth, Jupiter, Saturn, Uranus, and Neptune. 3 are missing, and the reasons are routinely swapped in retellings, so here they are correctly. Mars was lost to scattered sunlight inside the camera. Mercury was too close to the Sun to image safely. Pluto was too small, too far away, and too dark. Uranus and Neptune came out visibly elongated because the exposures were 15 seconds long and the spacecraft moved during them. Then there is the light in the Earth frame, which is the detail most people miss. The planet sits inside a broad diagonal band of light. That band is not real. It is not the Milky Way, it is not a nebula, and it is not anything in space at all. It is sunlight scattered inside the camera's own optics. Voyager was about 32 degrees above the plane of the solar system, and the Sun was near the edge of the field of view, and the result is an artifact of exactly the kind an imaging engineer would normally regard as a ruined frame. The most reproduced photograph ever taken of the Earth is a photograph in which our planet happens to be sitting inside a lens flare. That the two coincided is pure chance. Had the geometry been a degree or two different, the dot would have been on plain black background, and the picture would be less famous than it is. Now the argument, which took 9 years. Carl Sagan proposed the picture in 1981. It was taken in 1990. The reason for the delay is straightforward, and the people on the other side of it were not being obstructive. The picture had no scientific value. None. It would not measure anything. It would not test anything. Pointing the cameras back toward the Sun carried a real risk of damaging the Vidicon tubes, which were the only imaging system the spacecraft would ever have. Executing the sequence consumed spacecraft time, and more importantly, it consumed deep space network time, which is the scarcest resource in planetary science and which was in demand from missions that were still doing measurements. There were people who thought it was a poor use of a functioning spacecraft. By the standards they were applying, they were right. Sagan kept asking. For 9 years, across 2 encounters and 2 planets, he kept asking. The sequence was finally approved and executed on the 14th of February 1990, after Neptune, when the cameras had nothing left to photograph and there was no longer an argument against the risk. The data sat on an 8-track digital tape recorder for weeks. It came down over 4 separate deep space network passes and was not fully on the ground until the 1st of May. Picture the execution of it. The spacecraft is 6 billion kilometers out and climbing above the plane of everything. It has been flying for 12.5 years. Its cameras have not been used since Neptune, 5 months earlier, and they are cold. The command sequence arrives after a 5.5-hour crossing at the speed of light. The scan platform turns, slowly and deliberately, back toward the Sun that the spacecraft left in 1977 and begins working through 60 frames, sweeping across the whole system it has passed through. The giant planets it visited reduced to points. The inner planets it never knew at all. It takes the frame containing the Earth at 4:48. 34 minutes later, the imaging system is commanded off. The cameras that photographed Io's plumes and Miranda's cliff and the braided F-ring and Titan's blank orange face and Triton's geysers go dark for good. And in one of those frames, inside a band of scattered light that should not be there is a pale dot occupying about 1/10 of 1 pixel, which contains every human being who has ever lived, with the exception of the 24 who went to the moon. The cameras were never switched back on, and they never will be. There are 4 reasons, and all of them are true. The power and the onboard memory were needed for the instruments that would still have something to measure in interstellar space, and those instruments have justified that decision several times over. The camera control software was subsequently removed from both spacecraft to free up memory. The ground computers and the software that could read Voyager imaging data no longer exist. Nobody kept them. And after 36 years at cryogenic temperatures, nobody believes the optics would work if they tried. So this is the only photograph of the Earth taken from beyond the outer planets, and it is going to remain the only one. There is no plan to take another. Nothing is scheduled. Nothing is proposed. A reprocessed version called Pale Blue Dot Revisited was released in February of 2020 for the 30th anniversary, produced by a JPL engineer named Kevin Gill, with input from members of the original imaging team. It is a cleaner rendering of the same data. There is no new data, and there will not be. There is one more connection worth drawing before this list closes, and it runs all the way back to number 5. Voyager 1 was 32 degrees above the plane of the solar system when it took that picture. It was up there because of the Titan flyby 10 years earlier, which had thrown it out of the plane. The decision to give up Pluto in order to look at a moon that the cameras could not see is the same decision that put the spacecraft in a position, a decade later, to look back down at the entire solar system from outside. And there is a connection to number 9 as well. The image that revealed Io's volcanoes was an overexposed navigation frame, taken to ignore the moon and photograph the stars behind it, in which a crescent of light off the limb turned out to be something nobody had expected. It was an accident, spotted by someone who was willing to work out why an artifact would be lit. The image at number 1 is also an awkward exposure, pointed somewhere the engineers would rather it had not been pointed, containing a lit speck against scattered light. The first was an accident that revealed a world. The second was a decision that revealed the people who built the machine. And one last piece of arithmetic, because it closes the circle this list opened with. Each Voyager image is 800 pixels by 800 pixels at 8 bits per pixel. That is 5.12 megabits, or 640 kilobytes. The total computer memory across all 6 of the spacecraft's computers is 69.5 kilobytes. Every single photograph either spacecraft ever took is about 9 times larger than the memory of the machine that took it. They could not be stored. They were written straight onto an 8-track mechanical tape recorder holding about 100 images, which has been running in vacuum since 1977, and then played back to Earth slowly, one at a time, over hours. That is what took the picture. 69 kilobytes, a tape drive, and a camera designed in the 1960s, 6 billion kilometers from the nearest person. It is worth being precise about how small 12/100ths of a pixel actually is, because the phrase slides past the ear too easily. A pixel in that camera is not a fine grain of detail. It is the smallest unit of information the instrument can resolve, and at that distance, a single pixel covers an area of space far wider than the Earth. The planet did not fill one. It filled a fraction of one, and it registered at all only because it is bright, because it is white with cloud and blue with ocean, and because it happened to be sitting in a part of the frame where the scattered light did not wash it out entirely. If a finder somewhere ever decoded the images on the golden record, they would find photographs of the Earth taken from close range, showing coastlines and weather systems and cities. Those images are on the same spacecraft that took this one. The difference between them is not the camera. It is the distance, and the distance is only 6 billion kilometers, which on the scale of the record's own uranium clock is nothing at all. There is also the question of what the picture is for, since it measured nothing. The argument that eventually won was not scientific, and it was never presented as scientific. It was that the species should see itself from outside once, while there was still a working camera in a position to do it, because there might not be another opportunity and because no one alive had ever seen it. That is not a hypothesis. It is not falsifiable. It does not belong in a mission proposal. And it turned out to be correct in the narrowest, most practical sense, which is that the window was 34 minutes wide, and it has never opened again since. Everything that has been photographed of the Earth from space in the 36 years since has been photographed from close by. From low orbit, from the Moon's distance, from Mars in one case. Nothing has been in a position to look back from beyond Neptune with a working camera, and nothing is going to be for a long time. New Horizons is out there, and its camera works, but it has other targets and a different mission, and the geometry is not the same. So the only photograph of our planet from the far side of the solar system was taken on a Wednesday in February of 1990 by a spacecraft that was already 13 years old, over the objections of people who were entirely right about its value as data, 34 minutes before its eyes were closed for good. So the list ends where it does. Two machines, built with less memory between them than one of their own photographs, launched 11 weeks apart in 1977 for a 4-year mission, which found volcanoes on a moon nobody expected to be active, an ocean under 20 kilometers of ice, the tallest cliff anyone has ever measured, geysers at 38 Kelvin, and the outer boundary of the sun's influence. And whose last act with a camera was to turn around and photograph the people who built them, from a distance at which those people could not be seen. Both are still traveling. Both are still transmitting, faintly, in the 2 senses each has left. And somewhere ahead of both of them, in about 40,000 years, there is a star neither will reach. Sleep well, and good night.